Welcome to everyone for the WCRP meeting on Future of Climate Modeling Workshop. My name is Vaishali Naik, and I am based at NOAA Geophysical Fluid Dynamics Laboratory at Princeton in New Jersey, and I'm also a co-lead of this workshop. And I'll go over some of the technical guidance and housekeeping items to help us smoothly navigate and run this workshop. So, all right. So in terms of technical guidance, please remember to turn off your microphone unless you're presenting, you're a chair, rapporteur, or you've been asked to speak. For any technical assistance, please chat with Nico Caltabiano via Zoom chat, who's on this call. And in terms of Q&A and discussions, please use the raise hand option to ask questions or share comments in the open discussion sessions. You're also welcome to add questions and comments to the Etherpad for broader discussions. The picture on the right shows the screenshot of the Etherpad. This is what it'll look like when you log in. And all you have to do is just start typing under the title of the talk that you're going to ask questions or comments about. So please do not use Zoom chat for discussions. We'll be tracking either the Etherpad or the raise hand options. All speakers are encouraged to respond to questions and comments on the Etherpad after their talk. Time permitting, the session chairs may select some of the questions of greatest relevance and interest to bring up in the discussion sessions. For timekeeping, we request the speakers to be within the time limit, and the session chairs will provide a verbal cue when 2 minutes are left. So in terms of the session summary reports and the breakout group reports, the rapporteurs will provide their summary reports. They have an important role to play here. We will assign rapporteurs in advance. Some of them have already been assigned, but in case a session does not have an assigned rapporteur, we request the session chair to seek volunteers at the beginning of their session. As Nico mentioned, the workshop is being live webcast or streamed on the WCRP YouTube channel. The link is available on the WCRP website. And we also request everyone to only share the workshop webpage on the WCRP website with your colleagues and not share the Zoom link. So in terms of the program today, here is a little summary. For today and tomorrow, we have 2 oral sessions each, where we'll be hearing from the speakers in the 2 sessions. Each of these sessions will be followed by discussions. Tomorrow, we also have lined up 3 breakout groups. And then on Wednesday, we have a summary reports from the different session rapporteurs, along with discussions, and also additionally 4 breakout groups. And finally, on Thursday, again, we'll be recapping the previous day's sessions, and we'll be looking forward in terms of our writing task for the white paper. Each day ends with a wrap-up plenary, and breaks are included each day depending on the schedule. So for today, we have right after I get off the screen, Detlef will give us an introduction and set the scene for the workshop. Piers Forster here will go over the workshop aims, including the input we received from everyone on the survey. And following these, we'll have 2 sessions with exciting and provocative talks. First, on the challenges of climate modeling, and second, on societal needs for climate information. And before I hand off to Detlef, I wanted to say very thank you to our speakers, our chairs and rapporteurs for agreeing to take on these roles. To everyone for responding to the survey to inform this workshop and set the strategy for WCRP's future climate modeling. And a big thanks to Nico for his support and assistance in organizing and running this workshop, and also to WMO for hosting this workshop. So with that, over to you, Detlef. Detlef, we cannot hear you.
Thank you very much, Vaishali. And let me actually jump in right away. And first of all, as the chair of the Joint Scientific Committee of the WCRP, let me actually all welcome you. And that means the people online, but also the broader audience. In fact, we have now almost 90 people online, and this is already a great success. I do want to give a little background to this workshop, and going back to February 2020. In fact, it was just before all the doors closed because of COVID-19. We had a very successful workshop run in Hamburg, the kind of infamous first Hamburg workshop, where we basically thought about how we turn the new strategic plan of WCRP in really a science and a new structure. And very important development actually came out of this workshop, among them the so-called lighthouse activities, which approach now very important topics that have urgency in the whole development of information. It also did lead to a very important restructuring of WCRP and among others, in fact, the introduction of a new core project, which we now call ESMO, Earth System Modeling and Observations, bringing together all the modeling and observational aspects of WCRP. And it was already clear at this point of this workshop that the future of modeling, climate modeling within WCRP, but also more generally, really also needed a lot of attention and brainstorming, such like this first Hamburg workshop, also on the modeling, where it goes. It was obvious that there are different opinions, different strategies, different many things. And so it was really obvious at that point already that we have to do a workshop on the modeling, kind of starting with a white paper and see where we want to go. And because of COVID-19, actually took now almost 2 years to come together, and we are here now at the beginning of this workshop. And already in Hamburg, it was clear that we need to discuss climate modeling, the needs that go beyond CMIP, really where the cutting edge problems are, the frontiers, if you want. New technologies need to be taken into account, capabilities that really didn't exist in the past, but will actually allow a huge new enabling aspect of modeling. Significant model development and improvement is required, including, in fact, bias reduction. Conceptually, the field needs to understand the needs for trade-offs between model resolution and ensemble computations, really what the field, the information is required. And we need to improve diagnostics that really lead to actual information for decision makers. And that's kind of under the buzzword co-design. And I think this is all aspects that really need to be addressed in this workshop. And essentially going back a step, out of COP21, really it was obvious that we need to develop much more actionable climate information, and that is related to climate science in a wider sense, but also to the modeling. And I think we will address some of these aspects here, or initiate the thinking along these lines. And so I'm really looking forward now to the discussions, really thinking out of the box, a fresh view on climate modeling and where we want to be in 10 years or 15 years. Of course, this will go into the planning of this new core project ESMO for defining the science for ESMO, but I think it will also go beyond WCRP. So during the workshop, we might want to, in fact, also address what of these challenges WCRP should actually approach or take into consideration as opposed to others, and so how we, in fact, divide this. And one aspect, we are not dealing much with observations here, but we are aware we need to deal with this as well, but this will come to at a later workshop. Just two more slides, very briefly information. There's a lot going on, and Björn Stevens unfortunately cannot participate because he's actually giving a keynote at NVIDIA workshop. I mean, it comes from really the game industry that wants to put $500 million into developing climate modeling, or the hardware for it. And maybe one or the other of you might want, in fact, to listen in over the next few days into these other sort of the parallel workshop. And my last slide, I want to remind you all that there's an Open Science Conference coming up, October 23, and I'm pretty sure that a huge part of that conference, Open Science Conference, will definitely also deal with climate modeling, and I'm looking forward into the advancements that we actually will reach until then. And with this, over to you, Helen.
Detlef, and we'll go straight. Thanks, Detlef, and we'll go straight to Piers for his presentation on workshop aims.
Yes,
Piers,
absolutely.
the floor is yours.
Yeah, good afternoon, good evening, good morning, everyone. I am the kind of co-host of the workshop, and it's fantastic to have everybody here today. I'm really sorry we can't meet together in person, but I think it will still be a very exciting time. And the advantage of meeting over the internet is that we can have far better representation from lots of different countries, but it does mean we have to get up at awkward times to come to the workshop. So I do really appreciate those coming at odd times of day. So the first thing I want to say, I think we have a huge amount to celebrate as a community. I mean, the forefathers of climate modeling, Suki Manabe and Klaus Hasselmann won the Nobel Prize in 2021, and I think that gives us enormous sense of credibility of kind of what our work has achieved. So I think we have a huge amount to celebrate, and so it's a good time to reflect as well. And the other thing, I think we've also persuaded the world to take action on kind of climate change. Perhaps in not taking the fight action we wanted to, but the world has definitely moved from trying to understand it to try and take action, and that's we need to change perhaps the way we reflect on that. And the other thing, both kind of Vaishali and I have just come off authoring the Working Group 1 report of the IPCC, and if you have a look at that report, yes, the CMIP 6 results were integrated throughout that document, but if you look at the headline conclusion from that report, they in fact would have probably been identical if we hadn't had the CMIP 6 exercise at all. So what I think these three things tell us is that I think it's an important time for us to reflect as a kind of community, kind of why we are doing what we are doing, and kind of what our purpose is, and kind of where we want to go together. And I can't go forward for some bizarre reason in my. I seem to be stuck on my. Sorry about that. I don't know why I can't go forward.
You want me to share the slides for you?
What I can do is just go like that, okay, and then go forward like that. I kind of wanted to really share this picture of Suki Manabe and Joe Smagorinsky, the first director of GFDL, and this is a fantastic picture from 1972, and it's interesting to reflect that if you have a look at it, things haven't changed an awful lot, perhaps. In a certain way, they've changed hugely, but in a certain way, things haven't really changed at all. We are still getting together with our friends and producing plots and going, look at that, that looks interesting. Anyway, I thought I'd put it up there. Yeah, so the aims of the workshop are really trying to define where our community wants to be in both kind of 10 years time and perhaps kind of beyond that as well. And then importantly, we want to outline what we want to do to try and get from where we are today to where that will be. And I'll be really keen for us to produce a white paper document, and also to produce a kind of paper that goes towards a peer review publication. We can discuss what that would be like. And I want us to enjoy this workshop, to enjoy our kind of company of our kind of company, our colleagues, and really have the time to have a very frank and open discussion and some of this important reflection. But I absolutely appreciate the time and effort people put into submitting some brilliant kind of comments, and I really then try and kind of summarize them. I'm going to urge everyone to really go and have a look at everybody else's kind of comments. They are really interesting. But it's really obvious that we as a community really want to have our cake and eat it. We want higher resolution, we want more physics and chemistry in there, more accuracy, more ensembles, more diverse approaches. We want to have it from a more diverse community involved. We want to make them more accessible for everyone to access. And we want to all do this with less of a carbon imprint. So it's going to be a big challenge. And if you go over the comments, there are some things beginning to emerge. Definitely the theme about adaptation and trying to provide for the adaptation community is quite coming out from the work as well. There's also the acknowledgement to look more at extremes and tipping points in particular, and then the trade-off between whether to go for one digital type approach or whether to do model kind of hierarchies. And then people understand we have to get more involved in machine learning and things, but there's also some kind of doubt about that too, perhaps. And I think all these tell us together is that we have a job to do over the next 3 or 4 days to really try and set the kind of benchmark with what we're doing together. And I think this workshop won't be definitive, but I think it will hopefully be the beginning of a discussion that go on to really influence the community. So with that, I talked for too long already. It'd be tough to keep everything to time, but I will shut up, and I hope we have a really good workshop. Cheers, everyone.
Thanks, Piers. Thanks, Detlef, for setting the scene so nicely. My name is Helen Clue. I am the Vice Chair for the WCRP Joint Scientific Committee, and I'm chairing this second session, which is our first sort of scientific session on the challenges of climate modelling. Because time is tight, I'm just going to dive right in. We've got 7 great talks that I think are going to be really stimulating and inspiring. Each of them will speak for 10 minutes. We will do the Q&A at the end of the session, not after each speaker. But please do start putting your comments and discussion into Etherpad. I know some of you are already doing it in the chat. If you'd like us to be able to have this as a record of the session, it would be good to put that over in Etherpad. So without any further ado, let's get going, and I welcome our first speaker, Ruby Leung from the Pacific Northwest National Laboratory. Ruby's also one of our explaining and predicting Earth system change lighthouse people, and she will speak to us on ultra high resolution modelling. Ruby, the floor is yours.
Thank you very much for the opportunity to present. So let me share screen. Okay, so all right, so I was asked to give a presentation on ultra high resolution modeling. So first of all, let me define at least what I mean by ultra high resolution modeling. I think for the atmospheric model, we are talking about resolution definitely higher than 10 kilometers, a few kilometers, so that we can explicitly resolve convection and perhaps even clouds. And then for the ocean, we're talking about eddy resolving type of models. So just in case I run out of time, because there's only 10 minutes, so I'm going to put up 3 simple key messages from my talk. So what I will be talking about, essentially that ultra-high resolution modeling is a useful tool to add to our Earth system modeling toolbox, but we need many different tools in order to address the different facets of climate science and provide actionable climate information. And then the second point, I think we have learned that without much tuning, ultra-high resolution models are already very skillful and definitely more skillful than their lower resolution counterparts, but still there are some efforts needed to address model biases. And then the last message, I think there is more research needed to help to explore the different uses of these type of ultra-high resolution model and demonstrate the usefulness of these models. Some examples are given here, but definitely I would not have time to talk about all of these except maybe for one or two examples. So with that, so why do we need many different tools besides ultra-high resolution model? I think the reason is pretty clear to all of us, that we have many challenges that Earth system model is facing because there are many uncertainties from many different processes in the Earth system model. For example, some uncertainty might be coming from how we model the subgrid processes of convection, clouds, and aerosols, and they are particularly important for climate sensitivity as well as water cycle changes. And then also uncertainty related to carbon and nutrient cycles and the human influence on these cycles. And they are important, especially for projecting the longer term, the warming in the future. And then there are also uncertainty related to modeling ice shelf and ice sheet instability. And they have a lot of implications for projecting sea level rise. And then lastly, there's also large uncertainty coming from internal variability. So with all of these different challenges, I don't think that ultra-high resolution modeling is the only solution to all of them, but it's definitely a useful tool, for example, in addressing uncertainty related to subgrid processes. Another example that I like to mention why ultra-high resolution modeling might be useful is particularly for projecting changes in extreme weather events. So a UN report in 2020 showed that in the last 20 years, natural disasters have already increased significantly. And you can see a large fraction of these disaster events are related to floods and storms. And we'd like to know, of course, how floods and storms may be changing in terms of the frequency and intensity. But also more importantly, we also need to understand how storm structure may be changing in the future, because changes in the storm structure has implication for infrastructure planning. So this is based on a high resolution modeling study that we did, and we find that for the Western United States, the winter storms are showing sharpening of the storms, meaning that the peak intensity increases with warming at a higher rate than the area, and suggesting that it might affect the area intensity relationships, which are really important for infrastructure safe design. And high resolution model is important for resolving the storm structure. So for E3SM, which is the Department of Energy's Energy Exascale Earth System Model, we develop and run our model at a range of resolutions on different DOE computers. For example, we have low resolution models that we use to contribute to the CMIP deck. We also have high resolution model that we contribute to HIRES-MIP, as well as more recently, we have this global cloud resolving modeling capability. Our model also can be used to run high resolution using regional refined meshes. And for these, two examples are given here, where we put high resolution over North America, or we put high resolution over Antarctica. So now back to the main theme of ultra high resolution modeling. So as I mentioned, we have this capability now with our model to do very high resolution simulations. And I particularly want to call out Peter Cotwell, who is leading this effort for our project, and they deliver this capability of a non-hydrostatic dynamical core. We are targeting roughly about 3 kilometer grid spacing. The model can be run globally at this resolution, or zoom into this resolution using regional refined meshes. our Fortran 90 version has been used to participate in Diamond 2, and I'm going to show you some results. A lot of the results are already reported in Codeweb et al. Shown over here. We also have a version of our model where our dynamical core is written in C++, and that allows us to achieve a pretty good performance on a pre-exascale computer called Summit, and we can get to roughly about 1.4 simulated year per day. And this is the best performance we know of a cloud resolving die core with about 10 tracers at this kind of resolution. We are, of course, also targeting GPU-enabled version of our model, which is written in C++ with the Cocos library for performance portability. So we are actively working on this, and we'll have a operational version of this this year, so that we can run our model on exascale computer. So this version of our model will be called E3SM Atmosphere Model EMXX, standing for C++ version. So now I'd like to show you just an example of some of the results coming from our Diamond 2 run, which is a 40-day simulation globally at roughly 3-kilometer resolution. So with this Fortran 90 version running on a computer called Cori KNL, we achieve a performance of roughly 4 to 5 simulated days per wall clock day. And without much tuning, our model is already producing pretty reasonable results. In the simulation, we see a lot of atmospheric rivers producing really heavy precipitation. Our model also able to simulate really well stratocumulus, for example, off the coast of South America, as well as much better improvement in terms of simulating the probability density function of precipitation rate compared to lower resolution model. Furthermore, we look at our simulations for simulating these mesoscale convective systems. These are the largest type of thunderstorms, typically associated with extreme precipitation. You can see these white blobs over here. These are mesoscale convective systems producing heavy precipitation. So comparing our model simulation at 3 kilometers with observation, we can see the model is able to simulate a lot of these MCSs over the tropical ocean. So looking at these MCSs in our model, particularly compared to our high resolution model, which is 25 kilometers that we contribute to CMIP, we are already seeing much better simulation of the MCSs. For example, many of the observed MCS characteristics and the relationship with the large-scale environments are reasonably reproduced. Although we do see some negative biases in terms of the number of MCSs simulated by the model. And we see that this is partly because of the fact that even at 3 kilometer resolution, our model still insufficiently organizes deep convection into mesoscale convective systems. And as a result, the MCS rainfall amount and also the fraction of MCS rainfall contributing to the total rainfall is underestimated. And this is compensated by having more unorganized deep convection rather than organized deep convection. But also more broadly, more broadly, we also look at the Diamond 1 simulations, which is also 40-day, but for the boreal summer. We look at 3 different convective regimes in the stratocumulus regime, as well as the moderate and the strong convective regime. We see that these models typically show a lot of drizzles still at this kind of resolution, a lot of drizzle as well as light precipitation and not enough heavy precipitation. So this issue of drizzling remain, and with implications for cloud forcing and in the hemispheric asymmetry of the energy input because of the intrinsic distribution of these different types of convective systems. Lastly, I'd like to show one example of using this type of ultra-fine resolution for storyline development. So here we are showing a particular case of June 2012, a derecho swept through eastern United States, causing a lot of damages to power power lines and transmission infrastructure. So we use a resolution with variable resolution mesh down to 1.75 kilometer resolution. We're seeing that the model is able to really capture these strong winds as well as precipitation associated with the derecho. So with this type of modeling capability, we can ask how this specific derecho event may unfold in the future with warming. So with that, the key messages, as that I already mentioned before, ultra high resolution modeling is useful, but it's not the only tool in our toolbox. Without much tuning, these models can be very skillful, although there are some efforts still needed to address model biases. And there are many different uses of the models. And I think the community needs to really start thinking about what are the uses of these very computationally expensive models and what they can inform us for in the future. So with that, thank you very much for your attention.
Thanks, Ruby. That's great. Great key messages there. And I'll now move straight to our next speaker, which is Tim Palmer, who's from Oxford, who will talk to us on next generation climate modelling. And he's just sharing his screen. And I'll just say one more thing while he gets into presenter mode. Some of you are asking about whether the talks will be made available. We will talk first with the speakers, and we will let you know after the workshop which talks are going to be available. But it also, I think, the YouTube clip will be available as well afterwards. Okay, Tim, over to you. Thank you.
Okay, thank you very much. Can you see my slides okay? And
yes, we can. Yes, we can
okay,
hear you
great.
and we can see you. That's great.
Super. Okay, so thank you. I'm going to, the brief was to be challenging and provocative, so I'm going to dive straight into challenging and provocative. If there is a single take-home message from my talk, it's please, please, please think big. And I would just remind you, two big science projects of recent years were the Large Hadron Collider with a development cost of around 10 billion and the James Webb Telescope with a similar development cost of around 10 billion. And I just want you to ponder the question, is understanding, predicting our climate really so much less important than understanding or predicting the world on quantum or cosmological scales? I don't think it is, and therefore we need to be thinking about this sort of level of investment worldwide to a new type of prediction capability for climate. And it's kind of relevant because we're in the age, or we're about to hit the age of exascale 10 to the 18 flops computing. Arguably, we're already here in 16-bit arithmetic. Fugaku probably is close to an exaflop in 16-bit arithmetic for certain applications. So what are we planning to do with dedicated exascale computers? So I came across this news item a couple of years ago that Hewlett-Packard will be delivering the DOE with a 2 exaflop machine in early 2023, now named El Capitan. So what is it going to be used for? It'll be used for enabling advanced simulation and modeling to support the US nuclear stockpile and ensure its reliability and security. And to be perfectly honest, these are the main applications of dedicated exascale computers. Are we content with that? I would argue understanding climate is of equal importance to simulating our nuclear stockpiles. So the question is, what could we achieve if we A, all work together, and B, and I put this in red because it's something that we scientists perhaps fail to do adequately, persuade our governments that we need this type of investment to make reliable regional climate projections. So I've highlighted a few countries that could easily, or in the case of Europe, let's say a continent, who could easily afford to fund dedicated exascale computing for climate, and question mark, question mark, question mark at the middle there is put your own country in if you think it too can do so. What could we do with that if we were to, under the, let's say, scientific guidance of WCRP, develop a coordinated activity, a coordinated network of such climate institutes? And we could do the sort of thing that Ruby just talked about in the last talk, but in terms of an ensemble rather than an individual modeling framework. And we know from everything that we've done in the last 50 years that ensembles are vital if we get reliable predictions in meteorological or oceanographic variables. So this is something we can seriously, I think, envisage if we can, put our minds to it and work together. A kilometer scale global ensemble for multi-decadal climate prediction. Well, we've already had some of the discussion about why high resolution is important. I think first and foremost, it's that one is simply representing the underlying laws of physics more accurately. We get systematic errors because we have to truncate the laws of physics. We think we understand the laws of physics at their partial differential equation level. The inaccuracy comes when we truncate them. The smaller the scale that we truncate them, the more accurately we can represent these laws. In particular, if we go to, let's say, order kilometer resolution, then we can remove some of the three most important parameterizations of deep convection, of subgrid orography, and of ocean eddy mixing. And that will lead to smaller systematic errors. Hopefully, we don't know, but hopefully it will lead to errors which are systematic errors which are finally smaller than the climate change signals we're trying to predict. Currently, in current simulations, that's not the case for regional variables such as precipitation and even temperature. Systematic errors are larger than the signals we're trying to predict. And in a nonlinear system, that's a recipe for unreliability. And of course, at higher resolution, we'll get better representations of extremes, and that's got to be vital for any adaptation applications of model predictions or projections. And a point I want to make, which is not typically made in these kind of climate type talks, but I think is absolutely vital, and it links into Detlef's comments about observations. We do indeed spend quite a lot of money on observations, particularly space-based observations, and yet we assimilate these observations into models that really cannot represent much of the information in the observations on scales that the models can't actually represent. So it's my belief that, for example, in numerical weather prediction, much of the initial error of particularly of forecast busts occurs because the model cannot assimilate the information from the observations on scales which are important, which can often be on convective or organized convective scales. So improving the accuracy and resolution of our models will actually lead to much better ability to assimilate observations, and hence to more accurate initial conditions. And this will be both the atmosphere and, of course, the oceans. And if we're thinking about a kind of mixed, say, decadal prediction of both natural variability and forced variability, having accurate initial conditions is vital. And if we have more accurate initial conditions, we're going to have much better reanalysis products for climate diagnostics. I'm sure anyone who's done reanalysis diagnostics will know that, particularly for diagnosing extremes, they have certain limited value, I would say. And so we're going to improve on our ability to diagnose climate. And there will be spin-offs for the CMIP class models. I'm certainly not suggesting that we stop that development, and hopefully 1 kilometer data will help us improve how to parameterize. Unquestionably, in my view, it'll be stochastic, but parameterization of CMIP class models. So there's a lot of, and Bjorn and I wrote a paper in PNAS a couple of years ago on all this sort of stuff. So we had the already the kind of difficult question about what's the right balance between high resolution ensembles and Earth system complexity. And there's a kind of an implication that going for all three is sort of impossible or incompatible. But I disagree with that. I think, again, if we think big, we can do all three. But I would just make 2 minutes. Okay, thank you. I would just make the following point. In Oxford, we've done quite a lot of work on motivated by stochastic parameterization, by the way, quite a bit of work on reduced precision modeling. And there are 2 papers which have come out relatively recently, one on emulating 16-bit precision in a climate model, and then the one on the right is an actual emulation of shallow water model on an ARM A64FX chip at 16 bits. And we firmly believe there is a role for 16-bit computation in climate modeling. If you believe the marketing of NVIDIA with their GPU tensor cores, we can expect up to 32 times speed up of 16 bits over 64 bits. It's kind of quite a nonlinear speed up for various reasons. And I think, for example, the cost of Earth system complexity can be reduced even more if we were to replace current Earth system modules with ultra-fast neural nets, which are basically matrix multiplications, ultra-fast, trained on offline Earth system models. There's a long way to go, I think, to reduce the computational cost of kilometer scale models. We shouldn't base current estimates of cost on current code. Dedicated exascale computers, I think, will allow small ensembles, or maybe of less than 10 members, of K-scale multi-decadal integrations. But if we could work in this sense of developing a federated network of coordinated multi-model ensembles, then we can look at greater than 50 members or more. And, we have experience of doing that sort of thing, obviously in WCRP and elsewhere. I worked with the Europeans on Demeter and ensembles, and of course CMIP is a good example. So this is my last slide. I think it can be done. I think for the sake of society, it must be done. And with endorsement by WCRP and active engagement by WCRP members in the coming years, it will be done. But providing we're prepared to think big, that's the kind of bottom line. Thank you very much.
Thanks, Tim. Thanks for that encouragement to think big. We're already getting lots of interesting discussion in the Etherpad, so that's great. And I now welcome to the floor our next speaker, Elena Shevlikova from NOAA GFDL. Elena, the floor is yours. If you can start sharing your screen, it'd be great.
I'm trying to share my screen now.
Okay.
The screen.
Yes, that's looking like it's working. If you just
let me just go into
presenter mode. Yep. Perfect.
Hello?
Thank you.
Okay.
Yes, we can
Hi,
hear you and we can see your slides. Thank you.
Okay, thank you for giving me opportunity to speak about challenges in Earth system modeling. I'm a land modeler, and often land becomes sort of the Cinderella, which the view that land doesn't matter, but it breaks everything. That's a common theme in my 3 generations of Earth system development. So this talk is collaboration among many scientists at GFDL, at Princeton University, at NOAA Cooperative Institute, USGS, and other collaborators. And let me start with definition of Earth system model. For purposes of CMIP 6 and in GFDL framework, we think about Earth system models as comprehensive physical climate models, which include atmospheric chemistry and fully consistent carbon cycle interactions. Such models could be run both from CO2 concentrations and from the CO2 anthropogenic emissions. And they also include new type of interactions in CMIP 6, such as like dust, iron, nitrogen interaction between different Earth system components. So if we think about CMIP 6 contribution, GFDL physical model will be CM4, and SM4 would be something that include much more interaction. So to me and to many of us at GFDL, it's all about physical and biogeochemical interactions and feedbacks. And you could apply this model both for decadal and century idealized historical and future experiments. As well, you could start to do prediction and predictability experiments. So I wasn't sure what challenge meant. Is it the goal, what we want to do, or is it what we have difficulty with? Let me start with what we actually see as a goal, or challenge as a goal. So we think that ASMs could be very useful and successful in assessment of coupled carbon climate feedbacks under potential climate mitigation scenarios, including both robust characterization of trajectories, limits of detection attribution, and uncertainties. We also need to understand what is viability of CO2 uptake by oceans and land, and what is ecosystem vulnerability. We also need to understand how the mitigation and carbon dioxide removal technologies can affect our biospheric sinks and how water would be feedback to climate systems. We also need to start to think about exploring seasonal to decadal scale biogeochemical ecological predictability, both for marine and terrestrial systems, and understand the climate risk due to extreme events, fires, droughts, and floods. And also, like, what is the implication of high resolution modeling for representation of the coastal biogeochemical interactions and different vulnerable land ecosystems? I guess the secret message here is that you cannot get at these questions with emulators. You really need to look at the spatial patterns, and you really need to add different spatial and time scales. Okay, let me just go quickly through, hide this. Sorry. Let me look at the, oops. I'll go back, hold on. Doesn't want to go back. Okay, go, sorry, just skip something. So if we look at the ESM challenges from marine ecosystem and ocean biogeochemistry perspective, GFDL models, as well as many other Earth system models, reach critical milestones. We now could represent ocean food webs connecting plankton and fish. There is a we can represent biological processes influencing the sequestration of carbon in the deep ocean. And we also could capture atmosphere-ocean nutrient exchanges. The challenges remain in modeling coastal biogeochemical interactions because these systems are complex, the processes occur on much higher resolution, and there is a freeway coupling between land, river, and coastal processes, including the runoff from the land of all sorts of pollutants, which can affect hypoxia and harmful algal blooms. Here in the bottom of the slide, you could see impacts of resolution on the ocean bottom temperature predictions. On the left, the CM2.5 resolution produces much smaller range of temperature than a high resolution model is CM2.6 in the resolution in the ocean. This is about like 5 to 12 kilometer resolution. This is 12 to 25 kilometer resolution in Atlantic. So resolution actually strongly coupled in the prediction of the coastal systems and in the ocean in general. So atmospheric chemistry. JFDL, as well as many other centers, have been successful in introducing very complex tropospheric and stratospheric chemistry interaction. We have 130 different tracers, for example, at JFDL. And these models can predict a variety of the chemical traces that interact with the land and the ocean. But going forward, we still need to increase interactability between the atmospheric chemistry components and land, ocean, BDC, and climate. For example, why does it matter? And if you look at experience of GFDL, this is an example where the atmospheric chemistry did make a difference for macro characteristics of the models. On the left, you see a small table here, ASM4 and CM4. They're different in terms of including this interaction in biospheric components. Transient climate response decreased substantially from physical model to ASM4 once these interactions have been included. And the same true about climate sensitivity. CM4 and ASM4 have the same atmospheric physics, the same ocean physics with different resolution, but one of the main differences is interactive chemistry. And you could see that inclusion of these different interactions, possibly through sea salt emission, temperature emission sensitivity, secondary organic aerosol sources from BVIC emission, dust emission, stratospheric ozone, have potential to very systematically in a strong way affect the macro characteristics, which substantially can affect all sorts of other predictions. Land. I am a land modeler, so I'm going to speak a little bit more about land. So current land components predict physical characteristic, plant soil temperature, liquid and frozen water, exchange to atmosphere and ocean. They project plants and soil carbon, CO2 fluxes between land and ocean due to land use and climate, nitrogen limitation. Typically, the climate models and ESMs use represent land climate human interactions through prescribed land use, land cover change scenarios. Very few models have internal sort of coupling between human management and climate. However, in CMIP 6, there is still very few models. I think there is only 4 models which represent vegetation dynamics, include interactive methane, biogenic volatile organic carbon, dust, and carbon aerosol emission interactions. Most of the models, like in CMIP 6, do not represent human water management, reservoirs or irrigation, just a very few, urban system, and agricultural management. So which, based on the literature, there is expectation that ASMs may underestimate the potential of land processes to amplify or attenuate climate change for positive and negative feedbacks. So one of the key messages that I want to get to this audience that so far emphasis in ESM land components was on increasing land biogeochemical cycle representation, nitrogen and phosphorus in addition to carbon. But there is very few efforts been done to include ecological comprehensiveness, both for plants and soil. So let me show you examples from our model. And what does it mean? So here on the left, you have projections of the carbon sink, which is a critical
Elena, you have 2 minutes.
Okay, so basically you have a key uncertainty about projections of the future carbon sinks. And most of models project increasing carbon sinks, particularly in tropics. Like from in 1990s to 2000, intact tropical forests accounted for about 50% of global land carbon uptake. However, our model projects losses of this carbon in all scenarios, from ambitious scenarios to baseline scenarios, and increase in the Northern Hemisphere carbon sink. So we don't know actually still where carbon sinks occur. This is major uncertainty in the system. So what do we actually know about the tropical carbon sink? Recent papers suggest that there is actually a decline in the observed carbon sink in Amazon, and there will be decline in the African carbon sinks. And decline happened because we don't actually, mortality of the trees increases in time. So here, these results from Hubaut et al. Analysis based on almost 700 tropical forest plots. So if we lose the Amazon, what would be implication for the global carbon cycle and for the climate? I'm gonna skip this plot. I'm gonna skip this. So we did some like a toy model experiments where we took the emission-driven ASM4 model and removed completely, due to deforestation, trees in the Amazon and in different scenarios. Here is the results for SSP 1.19. So this is the most sort of ambitious pathway. And what we find out that loss of Amazon would end up in a 1/4 degree warming compared to the traditional SSP 1.19 scenario, and increase in 30 ppm in atmospheric CO2 concentration. So which means that it's less likely that we're going to keep world under 1.5 degree since pre-industrial period, and we less likely to achieve Paris goals. So I don't think we actually understand what would be the changes in the carbon sinks in the future, particularly in tropics, because it's complex interactions and feedbacks. And there is I'm not going to go through this list, but as what we found in the special report on the climate change in land, that there is a large uncertainty still in understanding of major drivers of the carbon sink and the climate feedbacks, including CO2 fertilization. We still don't know what is the magnitude of CO2 fertilization and other drivers in controlling the global carbon sinks. We don't understand how the carbon vegetation and land surface models can capture the adequately tree mortality, which is a key process in representing the future of carbon storage, and how the drought is going to affect the vegetation. We also don't understand much about soil organic carbon, which is very hard to observe. You cannot get satellite pictures of the soil organic carbon. And there is complex interaction between additional little due to CO2 fertilization, which could be there, temperature, and the soil moisture. So all of these processes require rethinking about how we do carbon cycle science. We need more detection and attribution studies. We need to understand multiple constraints from observations. We also need to understand the sensitivity of the soil carbon in particular to different type of climate drivers. And I don't know, I think like going to 1 kilometer might help atmospheric processes and convection, but I don't think going to 1 kilometer resolution model are going to help us to understand what the future carbon cycle will be, because I think we're missing fundamentally constraints on many processes which control the future of that, of land And I think on the regional scale, the feedbacks from biophysical interactions are not well understood.
Thanks, Elena. Was that your last slide?
Yeah, I can make it last slide.
Okay, sorry to cut you off, but we do need to keep to time. We've got a full agenda, but thanks so much for sharing those really good insights into the role that Earth system models are playing in some of these key processes. So we appreciate that, and we'll have chance for more discussion at the end of the session. So now I'll invite Sabine Attinger from Helmholtz, Germany. And Sabine, if you could start sharing your screen, she's going to talk to us about hydrological and regional modeling.
Yeah, thank you very much. I have no problems to...
Would you like us to share?
Yeah, please,
version?
that would be really nice. I don't know, I have no problems.
Sometimes our computers just do this to us. Nico, are you able to bring up Sabine's talk?
Yep.
Thank you. And Sabine, you just do the next slide. Thing.
Yeah, sorry, I don't know why it
change.
doesn't work now.
That is it. It's the joy of doing meetings virtually. And that's why we do the backup. So
I'm sharing my screen now.
yeah, it looks like it's on its way. Yep, can see that. Just put it in presenter mode, Nico.
Okay, so
Perfect. We're seeing the speak. Yeah, that's it. That's right. Up on the top left hand, there's a display. Yep, that's it.
Now it works.
The floor is yours, Sabine. Thank you.
Okay, so thank you very much. So this talk is eventually a little bit exotic because it's now it will be about hydrological modeling, and I will present you a little tour through hydrological modeling, the connection to climate models, and in the end, I will come to the challenge Ruby was already mentioning, namely flood forecasting. So the next slide, please. Thank you. So let me first motivate our work. A particular focus of hydrologists is droughts and floods. And these two of the most devastating consequences of climate change. 3 billion people were affected in the last 2 decades. Many humans were suffering. And there were also huge economic losses. So, for example, if we have a look on droughts, so farmers were suffering from tremendous losses, yield losses, but also crop failures. There was water supply that has been shortened, and water quality was degrading, but also power plants had to be reduced, and due to missing cooling capacities or transportation on rivers was hindered. In floods, it's clearly so there was landscapes devastated, but also a huge amount of costs, billions of euros, were, for example, then the consequences of the AR flood in the last year. So then the next slide, please. To model and to predict, for example, floods, but also droughts, we developed our own hydrological model. It is called MHM. It is a grid-based, seamless hydrological model. On the right-hand side, you see, for example, it runs globally and predicts stream flow everywhere in the world. But it delivers also other state variables like soil moisture, evapotranspiration, or groundwater recharge. And it comes with a very unique feature, and this is what we call a multi-scale parameterization scheme. And with that, you can establish the model on a very fine grid resolutions of several hundred meters or a kilometer up to hundreds of kilometers. And the next slide. So this is where we started from 10 years ago. So in the very beginning, we worked with the North American multi-model ensemble, and we're feeding that into our hydrological model MHM, but we compared it also with a statistical approach called ESP here on that slide. And here you see, for example, one result. So if we want to predict or forecast soil moisture droughts, this ensemble worked already pretty well if we want to predict a drought 1 month ahead, but you also clearly see if it comes then to a prediction or a forecast 3 or 6 months ahead, then this accuracy is already vanishing. And next slide, please. There's also a reason why, at least in case of the forecasting of droughts, the system worked pretty well. You see here the capability to predict temperature or precipitation 1 month, 3 months, or 6 months ahead. And you clearly see that the forecast in temperature was very nice, also for 6 months, but precipitation was the problem. Now, for soil moisture droughts, temperature plays a very essential role, together with the capability of the hydrological model to start with the right initial conditions. But if temperature and initial conditions, hydrological initial conditions are well predicted or well modeled, then the capability of a forecasting system for droughts works already pretty well. Next slide, please. Yeah, and that was the start of building up so-called model change for predicting droughts, for example, and that helped the European project called EDGE. So built on an ensemble of GCMs from the CMIP. The precipitation and the temperature was fed into different hydrological models, and they then delivered in the end soil moisture. And then the next slide, please. And with that modeling chain of these ensembles of climate models and hydrological models, we were very good in predicting.
Oh, we seem to have lost you. Are you back?
Yes, I wasn't sure that was me or whether it was Sabine. Sabine, are you still there?
We seem to have lost.
I think we've lost her connection.
So we
do we go to the next talk?
Yeah, I think we might. I don't know if we can get a. Yeah, I think we better had really. Do you know how much more she had in her kind of PowerPoint?
Yeah, Nico, how much more did she have?
Suggest we go ahead and give her a chance to come back if she comes back. She's frozen.
Yeah.
Yeah, I think she's halfway.
Okay,
I think we want to continue with the text talk, but we do come back to that time.
If we'll come back to her at the end. Yes. Okay. So Jean-Yi and Baylor Fox, if you could, I'm not sure, are you doing one shared presentation or you're 5 minutes each?
Yeah, we were going to do 5 minutes each, and I was going to start. Let me pull up the slides momentarily.
Okay. So we'll welcome Baylor Fox Kemper from the US at the Brown University.
Somewhere in the US, Baylor.
Somewhere around there.
No, Brown University. Got it all written down. Somewhere in the US, and he's sharing this talk with Junyi Lee from South Korea on IPCC AR6. Thank you very much. We can see the slides. Just put it into presenter mode.
Great, and I'm actually tuning in from Cambridge, UK, so I'm even not in the US at the moment, but yeah.
Thank you.
Oops, that's not the right button I clicked.
Slideshow.
There we go.
Yeah.
All right, so Junyi and I have been discussing by email some of the outcomes from the AR6 Working Group 1 assessment report and how that's made us think differently about models. And so we have this in two parts. The first part is really to discuss how, in particular, the process modeling chapters drew on a wider variety of models, and that changed the sort of context for how we interpreted the CMIP core models. And then the second part, we think about some of the challenges that come along with that broader assessment. And so when we think about the CMIP 6 models, you know, the deck and the scenarios were obviously used heavily, but so were the high-res MIP and PMIP models, which are, you know, broader MIPs. The FAF MIP, the ABU MIP came into play in my chapter, and that broadened the sense. There were a lot of MIPs this cycle, many more MIPs than in previous cycles, and that really helped in some of the process assessments. In addition, things like emulators, reanalysis, regional climate models, Cortex, and other process models like Glacier MIP and Ice MIP were used in a way that was really expanded the scope of the science that was brought to bear, and also the community that contributed to the papers that were assessed. So this is one good example, and I hope you can see my cursor. If you can,
Yes.
On the left, so this is showing sea surface temperature from the paleo periods over here on the left, comparing observations with the BMIP models. And then we have the historical model simulations compared to reanalysis of sea surface temperature. We see that there's a seamless transition through the high-res MIP models that are tracking on the SSP 585. Then when we go into the projections toward the end of this century, we split out to a suite of scenario-based runs, and then we have the extended MIP runs that go all the way out to 2300. So this is one of the examples that shows the scope of change that you can reach. Here's another one from chapter 7, showing the use of emulators and how emulators allow for these extended runs to go quite a bit farther, even beyond the extended MIP runs. And the emulators were important in both the understanding of what was going on and how basic the energy cycle was, but also in the sensitivity assessment and how that related to the 3 key metrics that were related to an assessed climate sensitivity. And then here's one last example, which is an ice sheet model. And so the ice sheet models, get run after the rest of the climate models had been run. And so the ISMIP started as late as possible, but even then there were only SSP 126 and SSP 585 models available to drive the ice sheet models. And so if you look on the right-hand side, you can see these error bars. If we had only had the ISMIP 6, we would have had this relatively limited perspective of what the potential ranges were for Antarctica. But when we use emulators, we were able to get all of the remaining scenarios in between those two. And when we use a different class of emulators with a different set of assumptions, we were able to get a handle on the uncertainty in the forcing and the uncertainty in how the ice sheet models worked that went quite a bit beyond what we were able to get from the full ice sheet resolving models themselves. And then the last piece that I wanted to touch on was just that, when we think about downscaling in both frequency and time and length scale, there's a wide variety of different models, not just the GCM box and the high-res GCMs, but the regional climate models and process models. All of those pieces are part of the extreme scaling scenario. So I think we want to keep this in mind as we think about the kinds of models that go forward. Maybe this isn't really all WCRP business, but to know and recognize that the CMIP cycle triggers a set of other high resolution, regional climate modeling, et cetera, process modeling, emulator efforts afterward is an important part of what went into the process modeling chapters. Juni, are you there?
Yes.
Right,
thank you, Bella. Following Bella's talk, I will address some of the challenges of climate modeling imposed on the IPCC assessment. I'm Juni Lee at Busan National University and Institute for Basic Science Center for Climate Physics. Next, please. The first challenge I'd like to address is improving the fitness for purpose of climate models to assess the causes of recent climate change and the future evolution of climate. The simulation models include new and better representation of physical, chemical, and biological processes, as well as higher resolution compared to the models used in previous report. This has improved the simulation of the recent mean state of most large-scale indicators of climate change. However, as you can see from the figure, considerable biases still remain in many variables, such as precipitation and atmospheric circulation. Further improvement in model physics and biogeochemical processes to reduce biases in mean climate simulation will make the models more fit for attribution and projection, especially at regional scales. Next, please. There has been advances in better quantifying various sources of uncertainty in AR6 compared to the previous report. In particular, single model initial condition large ensembles represent a crucial step toward a cleaner separation of model uncertainty and internal variability than available for AR5. However, the use of single model initial condition large ensembles remain limited in AR6 because of limitations in model numbers and also coverage of scenarios. Besides, additional model results are still becoming available. It's also important to note that some uncertainties are not or only partially accounted for in the CMIP experiment, such as uncertainties in natural forcings from solar and volcanic forcings and long-term Earth system feedbacks. Next, please. There has been a growing demand for the improved near-term information for risk management and adaptation. AR6 tries to provide more integrated and comprehensive assessment for near-term climate information. However, near-term projected changes, particularly in precipitation, are very uncertain because of internal variability, model uncertainty, and uncertainty in forcings from natural and anthropogenic erosions. Initialized decadal climate predictions can be used for better constrained near-term climate projection, but their usage in AR6 is still limited, except for global surface temperature and decadal climate, most of climate variability. Next, please. For the first time in an IPCC report, comprehensive assessment of future changes in global surface temperature, ocean warming, and sea level are constructed by combining multi-model projections with observational constraints based on past warming simulation, as well as the AR6 assessment of equilibrium climate sensitivity and transient climate response. However, for other quantities, such robust methods do not yet exist to constrain the projections. Thus, uncertainty quantification for their changes is based on CMIP projections and expert judgment. Better constraining future changes in other quantities beyond global surface temperature, ocean warming, and global sea level is an important next challenge. Next, please. The AR6 Working Group report has an expanded focus on regional information supported by the increased availability of coordinated regional climate model ensemble projections and improvement in the sophistication and resolution of global and regional climate models. However, several challenges in improving construction of regional climate change information are identified, particularly in the Working Group 1, Chapter 10. Among them, I'd like to mention two aspects. One is that compared to the increasing number of large-scale evaluations, there is a shortage of process-based model evaluations at regional scales to assess the fitness of the chosen models for specific purposes. The other is further studies are required to better understand the processes governing regional internal variability, such as the modes of variability and their teleconnections, and the local processes and drivers involved. Next, please. Lastly, I'd like to touch the issue on scenario selection and scenario feasibility. The core set of 5 illustrative SSP scenarios was selected in the AR6 Working Group 1 to fill certain gaps identified in the RCPs in CMIP 5 and covers a broader range of greenhouse gas, land use, and air pollutant features than assessed in AR5. However, several issues remain in the filling the gap. For example, there are some slight mismatch with the key illustrative mitigation pathways assessed in Working Group 3. The SSP 3 7.0 are above the pathway with current policy, and the SSP 2 4.2 is approximately in line with the upper end of the nationally determined contribution. CMIP 7 may consider filling those gaps. There has been a growing discussion on the feasibility of ICP 8.5. In Working Group 1 report, no likelihood is attached to the scenario assessed, although feasibility along different dimensions is an important concept in scenario research. Thus, it is usually not possible to combine responses to individual scenarios into an overall probabilistic statement about expected future climate in Working Group 1. However, this aspect may need to be further considered. Next, please. To conclude, a wide range of numerical models from physical emulators to Earth system models of varying resolution are used to investigate climate futures under a range of scenarios in AR6. Challenges still remain on adequacy and causation of recent climate change and future climate in some metrics. Deeper analysis of these multiple lines of modeling evidence benefits from better temporal alignment of the CMIP cycle with the IPCC assessment process. That's all. Thank you very much.
Thank you, Junli. That's really good. And just to let everybody know, we'll finish Sabine's, we'll go to the next talk, which is Jean-Francois and Matthew, and then we'll bring Sabine's talk in before Pierre's. So I hope that's okay with everybody. Thanks, Jean-Yi and Bela. And we'll go now to Jean-Francois Lamarck from NCAR, and he's also part of CMIP, of course, and he will be talking to us about CMIP and its successes and where to next. And this is a joint presentation with Matthew Zelinsky as well. So Jean-Francois, the floor is yours.
Okay. All right, thank you. So thank you for this opportunity, and thank you for this great discussion. This is all the framing that we are seeing here from all angles are really key in, I think, defining what CMIP could also achieve in the future. So one of the things I'd like to just bring is the overall framework of what CMIP has. But really the objective of CMIP is to better understand past, present, and future climate change from natural and forest variability in a multi-model context. So there is really that key element of understanding climate change within a multi-model context. So how do we really take advantage of people and structural uncertainty, large ensemble that need to be taken into account to get a statistical sense of the answers that are being provided by the different model. One thing that's been key to CMIP is really the definition of common experiments, and that started right from the start in 95. By on top of that being also very specific to idealized forcing experiments, the 1% CO2, for example. And that's really trying to identify what are the experiments that are going to be the most useful at demonstrating and providing the information that we feel we need to have to understand climate change. I think it's really important to understand, as we're seeing in all the presentations before, that CMIP has a dual role. It's both a scientific enterprise, but it's also a key element to support policymakers and decision makers in general. We're seeing more and more the use of CMIP results in the financial sector and all sorts of planning tools at all sorts of resolutions, whether that's the right way to do it or not. But that's what we're seeing. So there is a really important aspect of CMIP that we should keep in mind in the duality. And that we're seeing, and maybe unlike what Piers mentioned earlier, but there is, CMIP has played a critical role in supporting the assessment reports from and those CMIP simulations, and they've been used extensively in and I didn't change my slides just because you made a statement. But I'd like to not just look at it historically, but I think we also want to really understand what is the size of CMIP. And this is something that came out in the 2018 WCRP review, where there was just a basic understanding of what is something like CMIP costing in terms of, in this case, just actual dollars. And then they put the national investments of all the different countries to be about $3 billion that would probably be spent over the course of say 5 to 7 years, a standard cycle of a CMIP. So it's not quite enough for Tim to get the 10 billion that he would need, but there is already a very huge investment. And so this we have to remember that this is a huge investment. And so one of the key questions that I would like to have is, are we using this investment in the most efficient and optimized fashion? We've heard a lot of CMIP sakes, and currently, if you look at the data on ESGF, there's about 114 different models, different model versions coming from 44 centers. And the amount of data is staggering, about 10 petabytes. It's still growing. So there is a wealth of information. There is a wealth of modeling centers that are coming from a growing number of especially non-OECD countries. And I think this has a really important political aspects to it. There is the recognition of the involvement of all the countries into defining what climate change looks like, and especially bringing their own perspective on what are the science questions and the aspects of the climate change that they are the most interested in. So I think that democratic aspect of bringing all parties to the table is really key in making CMIP relevant to all in the definition of what climate change will look like and how people are going to be affected. We just finished the CMIP 6 survey, and I thought this might be a good time to really bring some of really preliminary data that we're seeing. Its survey was closed last week, and Eleanor was on the line, who is now the project office head, has put those slides together. In terms of the fraction of the respondents, huge amount of input from Europe, from the US, that covers about 75%. But what I'm saying is that the respondents cover actually 25% of outside of those big blocks. And I think that's a really key element of when we're going to try to capture how useful CMIP is. We have to also understand what people do with CMIP. And when I'm thinking here, that's also quite interesting, is that we're going to see that it's not just the modeling centers. It's not just about the modeling. It's about how people are using the data. Some of the things that we are seeing is that for the people who responded to the survey, and we're really trying to dissect who those people are, and not who personally, but the overall scientific focus of CMIP is actually providing them what they need to do the science that they need to do. So we might not be capturing everything. We try to reach as many groups as possible, but within the group of the people who responded, CMIP does provide the information that they need to do the science that they want to do. There's a lot of variability in who uses the different MIPs in CMIP 6. Scenario MIP is clearly a big one, but high-res MIP, DA MIP, and even AirCam MIP, and I didn't falsify those results. All those are really key for people to answer very specific questions. So I think we have to really keep in mind that we are trying with CMIP to answer a lot of questions, not just a limited set that might be related to future, like scenario MIP is looking into. Because I only have a few minutes, I could be talking about all this for a long time. I'm trying to bring a few conclusions and a few key points forward. So I really believe that CMIP has been central and continues to be central to the use of multimodal approaches to answer scientific and societally relevant questions. Whether it's through the assessment report, the publications, we've seen just beautiful examples of the kind of science questions in the previous presentation from multiple people, but what Baylor was showing was clearly and clearly of relevance. What the survey is showing at this point is that the scientific community is finding that there is useful and critical information in the CMIP 6 data. And so I think we have to
JF, we'll have sorry to interrupt you, we'll have to wrap up now. I mean, you can finish the slide, but just
right, that's right, that's my last slide. So CMIP 6 represents a very large investment worldwide with a growing participation of non-OECD countries, which I think is a key aspect. But how do we optimize those resources? And how do we maximize the relevance of the simulations that we're asking people to do and to generate data such that it answers the questions that we want to answer? And I think that's going to be the real question. And that's what I'm seeing that from input from this workshop, it will also be critical in defining the next phases of CMIP, is what is the balance between high res, low res, all those models, the whole suite of models, not just the coarse resolution model, but where does CMIP fit within the bigger picture? That's all I have.
Thanks, JF. Sorry to wind you up, as in end you a little prematurely there. We'll hand over now to the second half of this talk from Matthew from the UK Met Office. Floor is yours, Matthew. We can see your slides. Thanks.
Marvelous, thank you very much. Okay, I'm going to give you a brief run round of some of the CMIP infrastructure. This is based on work that's on myself and Paul Durack put together. We WGCM infrastructure panel co-chairs, or commonly known as the WIP. Okay, so CMIP6 has been incredibly successful in terms of, you heard JF talking about the number of groups involved, the amount of data we produced. One thing I just want to highlight there is an interesting plot showing how things have grown over the last few years. Again, we started off in 2019 with gradually the first data being added. That grew rapidly as everyone worked towards the IPCC deadlines. That sort of in late 2020 that grew quite rapidly. But since then, we've continued to get more and more contributions. And particularly in the last few weeks, we've seen an extra petabyte added of new data for the deck and scenarios. One of the big successes of CMIP6 has been the structure put around all this work. So the common data standards are put in place with tools such as CMOR to be able to enforce those standards, the data request and the MIP tables defining variables that people can use and what data is needed for what purposes. Many tools such as the PCMDI metric packages, metrics package and ESM-Val2 are building on that. They're leveraging those CMIP6 conventions to do valuable science and allow people to do science at large scale. A lot of other projects are imitating these standards set out for CMIP6. Cordex has a similar parallel set, and this really does enable services to be built on top of the core activities we're doing. More on that in a minute. We've also demonstrated the extensibility. So we have the zero emissions commitment MIP was added relatively later on, and COVID MIP runs added in late 2020. All this demonstrates how we can take this infrastructure and adapt it and build on it and sort of continue to leverage the investment we've made to do more science. Just a quick overview of the infrastructure to show you what there is and some links onto the more recent technology. So we've got the CMIP6 specifications at the bottom there, the things like the control vocabularies and the data requests and the like. Mod output is built from that and using the tools like the CMOR, produce the NetCDF files, we've got quality control tools, and that all ends up on the Earth System Grid Federation with its archive, the publisher, the catalogs, replication, and the services which sit on top of that to allow users to get at it. So we've got the old search pages, and there's a new Metagrid search interface if anyone was wanting to give that a try. We've got errata services so people know what's any issues with the data or where it's been changed or extended. We've got citation services linking that data to the people who've generated and to the papers that have been written on it and the derived data sets. If anyone wants to have a look at that, it's quite interesting to go and digging in there. Alongside that, more recently, perhaps new with CMIP6, is the introduction of co-located analysis facilities alongside the ESGF nodes. A lot of the big centers have facilities that local scientists can sign up to, and now particularly with activities like the Pangeo initiative, secondary cloud archives with large fractions of our data up on Amazon or Google Cloud, which scientists can then take advantage of to do analysis. Right, my last slide, where next? So we're expecting more projects to use these common or aligned data standards and infrastructure. We're thinking about how we go beyond CMIP to extend reuse that infrastructure for an activity me and Paul are terming CMIP 6+ at the moment. The next round of Cordex will come around fairly quickly, and we'll sort of, again, build on this again. But there's a whole host of independent projects around which will want to do exactly the same thing, so they can feed their data into those common analysis tools. Certainly in the UK and in the US, there are a whole host of model development projects which are looking to leverage the CMIP 6 investment. In the future, we may end up with a quite different structure to CMIP. This is something that we need to decide about what CMIP 7 looks like. Perhaps there'll be a small tight core of core experiments, a deck and a few extensions and the climate scenarios, and then other activities alongside that, extending that out, possibly separate a little bit in time to spread out the effort. But the infrastructure and standards we need to do this need to continue to evolve to facilitate this expansion, involve next generation science, and leverage emerging technologies. There's also going to be increased sort of need for data access and usage. We really do need to co-locate compute facilities with the data. For example, places like sort of Jasmine in the UK, Glade, and Lawrence Livermore in the US, TKZ in Germany and others around the world. Alongside this, the private and public cloud providers, such as those facilities provided by Amazon, Google, the Microsoft Planetary Computer, the Copernicus Climate Data Store, they will all have a role to play in this. We also need to make sure we do look into ensuring there is suitable facilities for all regions, particularly those without their facilities, looking at Africa and South America in particular. And we need to really think about new emergent technologies, how we can make good use of that, like cloud services, and game changers such as the introduction of cloud use, a lot of ZAR stored data, a new technology to many people, but there are now ways to build on sort of our existing infrastructure and marry the new and the old together. And so a library called Ka-Chunk is sort of very promising in doing that. That's all I got. Thank you.
Thank you very much, Matt. We will now get Sabine to come back in to finish her talk, and she's going to try sharing her own screen. Thank you, Sabine, for your patience, and we'll see if this works.
Yeah. So do you hear me?
Yes, we can hear you.
Okay, great. And let me try to share. Yes, now I think it works.
Very good. Yes, we can see your screen.
Okay. Let me just move to where we are. And so basically what I told you already, that our forecasting system for droughts worked pretty well. But let me just now move to the next, namely the floods I announced already. So coming to flood forecasting systems, we have built up a new modeling chain, building in this case now on ECMWF models based on the IFS. So we are now aiming for a higher resolution in time and space, and everything was now again given to hydrological models. You see them here, and they deliver us now in particular runoff or discharge we are aiming for the flood forecasting system. And now I would like to show you some slides more about the flood forecasting system. So this is a hindcast of a flood in the Mississippi in 2016. And what you see here on red is the measured discharge. And you see here this high peak in January 2016. This slide is very busy, sorry for that, but you should concentrate now here on the dark colors, the yellow, the violet, the blue, and the green, very close here to the peak. And you see that only one hydrological model was predicting 1 month ahead the flood in the Mississippi pretty well. The others were already pretty bad. And this worked only because it was a big flood and a big catchment. The picture then completely changes if you are interested in flash floods, like the R flash flood in Germany the last year. Here you see we don't speak about lead times of months, but only of days. You see in the middle of the graph the discharge, or the predicted discharge in the R catchment. Again, the red line is the measured discharge. Then the measurements failed when the flash flood proceed. But what we see that here in that prediction mode is that 5, 4, and 3 days ahead, it was not possible to forecast the flash flood. 2 days in advance, then at least we capture here with our hydrological model the increase, but the peaks are still far from what we have seen in the R flood. So what we definitely need, and here I come back to what Ruby said in the beginning of her talk or during her talk, that we need much, much better, higher resolved climate models to drive our flood forecasting system. And we need also real data to do a bias correction, or in case the model is so good that we don't need it in the end, that would be even better. And if we go to the ECMWF forecast, then we clearly see here the DVD was on the left-hand side. You see the observation of precipitation and that day, the July 14, when the flood was occurring. And the ECMWF forecast 2 days in advance were in the higher percentiles already predicting some of the high precipitation amounts, in particular in the 1990 and 99 percentile, but the location of these high precipitation fields were not exactly predicted, and also then was not perfect. So what we really need for this flash flood or flood forecasting system is a much higher resolution, and that convection processes are then really resolved. And with that, I come to my summary of the key message. And the key message is basically, if we are interested in drought forecasts, then I can say that climate model ensembles are working pretty well to drive our hydrological models. But in order to establish a skillful flood forecasting system, and this would be for us the next step, then we really need hourly precipitation. We need a convection resolving global climate models, and very important for us, a fast coupling of the climate model with the hydrological model. So far, everything is file transfer based, but what we really need is an online coupling between our two worlds, the hydrological model world and the climate modeling world. And we are very interested and fascinated by the Destination Earth initiative in Europe. And we are hopeful that then this online coupling will be part of that as well. Thank you very much.
Thank you, Sabine, and some important challenges there. And thanks for coming, surmounting our technological challenges today. So we'll go to the last presenter for this session now, which is Pierre Freblingstein, who is at the University of Exeter and part of WCRP's JSC, and he's just loading his screen now. It's great, we can see your slides, Pierre.
All right, can you hear me?
Yes, we can hear you.
Perfect, all right, okay, thanks. So when Pierre asked me to give this presentation, I had to double check with him that he was about greening climate modeling and not just greening climate models, which is what I'm doing usually. So bear with me. I mean, this is like, well, it seems like the first time I'm giving like such a talk on greening the climate modeling community. So I'll be controversial, and I'll try to start from the least controversial to the most controversial. You'll see. Sorry. So just a bit of context, but of course you all know this. I mean, we need strong mitigation. We'll keep warming below 1.5 degrees. This is 1.5 lines. 50% by 2030, 100% by 2050. I think, and I hope most of us agree that the climate science sector must be leading the effort in terms of emissions. So we should at least have the same ambition in terms of like greenhouse gas emissions mitigations in the near term. So what do we want? Well, we want green scientists using green computers to do green science. And when do we want it? Well, we want it now. All right, so I'll start with the green scientists, and this is of course ongoing thanks to COVID, as you know. So before COVID, before we were grounded, we were not exactly leading by example. I mean, the numbers on the right are the number of flights, domestic, intra, and intercontinental. In red is for climate change scientists, and in blue is for other field of science. It's from a paper from Whitmarsh et al. In ERL. So we are above the average scientist, and well, as you all know, the average scientist is well above the average person in the world. So we can't go on forever like this. Traveling across the world, and landing on every single continent many times in our life. Overall aim, in line with WCRP, is to reduce by 50% relative to pre-pandemic level. So need to keep meeting virtually as we do now today, and you see that it's actually working very well. We need to keep air travel to the essential things that cannot be done virtually. So just giving an example, obvious example, field trips, yes, of course. SSC meetings, well, probably not. Also, we need to prioritize air travel for those who need it most, which is largely, early career scientists, and probably, not that many people on this call tonight. Okay, we need green computers. So the top-end supercomputer are becoming faster, and in terms of gigaflops, there's the figure on the left side. Over the last 20 years, the gigaflops have been increasing. with new generation of computers. The doubling time of speed is 1.3 years. They are becoming more efficient as well, and the efficiency is computed in megaflops per watt. But of course, the rate of increase in efficiency is not as fast as the rate of increase in speed. The doubling time is 2.1 years. So essentially, if you do the ratio of the left to the right, the energy consumptions increase over time, and it's increased by almost a factor of 10 since 2010, over the last 10 years. For these are for the top top supercomputers in the world. Again, that's from a review from Kumi et al. In 2019. So it's a bit like we had, Volkswagen Golf in the 70s or 80s, and we are moving to the big Ford F series. They are more efficient. You see, you can move. What was more like 4 times more mass of metal with less than twice as many liter of benzene per 100 kilometers, but we are still emitting more CO2 into the atmosphere, as you know. So that's not sustainable. So we need green computers. So we need someone, first of all, to monitor the carbon footprint of the computing centers. And by computing centers is also data servers and everything that we need to do the simulation and sustain the data and everything in the long run. Use certified green energy suppliers, which might mean that the best location for a supercomputer, or like the supermassive supercomputer we all dream of, it might not be in your own country. And there were some articles saying, like, if you read the press, Iceland is probably the best place in the world to have like a massive supercomputer because they use geothermal, for example. When upgrading supercomputer, of course, consider energy efficiency, not just efficiency alone. And probably more important, which is coming on my next slide, is we need to use them wisely. So, and that's what I mean, green science. So I have a question to JF. And what was the overall scope 3 energy cost of CMIP 6 in tons of CO2, for example? Do we know? Do we have any quantification of how much CO2 was emitted for preparing, doing, storing, sharing CMIP 6? Suspect we don't know. We don't even know these numbers, and it's a bit embarrassing that we don't know. And for CMIP 7, should we aim to reduce the CO2 emission by 50% for CMIP 7 compared to CMIP 6, in line with what we need to do anyway globally to keep warming below 1.5? And then I'm going to, the more difficult questions about the science. We need to weigh the cost of doing the science versus the benefits of doing this. And I'm taking a few examples. How many scenarios do we need in the future for CMIP 7, for example? How many MIPS do we really need? How many ensembles do we need to run for every single scenario? How many scenarios do you need to reach as very high resolution? One, all? Do we need all modeling groups across the world to do everything, with each one of them doing this with the state-of-the-art model? Or do we have like a more efficient way to get organized across the world to do this, reducing the cost, but keeping the same or almost the same level of benefits? Or accepting that you might lose some of the benefits, but massively reducing the costs. And then I'll be like even more controversial. Should we focus more on climate science, which actually supports a green agenda? Should we focus more on what we can call the 1.5 to 2.5 degree window in the future? Should we focus more on the near term? Should we focus more on extremes events and so on? And maybe less, and when I'm saying less, I mean less, not zero, on much larger warming level, like anything between 3, 5, 6 degrees. Do we need that many scenarios on this? Likewise, long term, do we need many scenarios to look on the long term, or can we reduce and spend more of the energy that we use and require for CMIP 7 for things that are critical for decision and green agenda in the near term? So I think I will conclude just with one quote from Kenneth Boulding, which is, anyone who believes exponential growth can go on forever in a finite world is either a madman or an economist. Thank you.
Thank you, Pierre, for that really interesting talk. And speaking of finite, those of you keeping track of time will have realized that we haven't done a very good job of sticking within our time budget, but that's okay. We've had some really fascinating talks, and we will have lots of time for discussion. There's already been an enormous amount on Etherpad, so we've decided that we're going to not have a discussion session right now because we are over time there. So please go and continue having your discussions on Etherpad. We have time in session 4 at the end of today's session workshop for reflections, and we've agreed that we'll use that to take some questions as well. So right now we're going to take a break. So we've got 5 minutes. We're going to shorten the break to 5 minutes, and then we'll come back to the next session 3 on societal needs. But before you all go on your break, 2 important things. I want to thank my co-chair, Vaishali, who's been doing a great job of keeping time and also on Etherpad and managing all that for me. So thank you, Vaishali, for co-chairing the session with me. And I want to thank our rapporteur as well, Laura Wilcox, for agreeing to be the rapporteur for the session. And all of that material will come together. And don't forget to sign up to the breakout groups where we can continue having the discussion. So for now, a 5-minute break, which will, by my clock, mean we will be back in front of the computer screens at 10 to the hour in whatever time zone you are, except for those who are on the 30-minute time zone, but I'll let you work that out. So a 5-minute break, okay? And then we'll see you back here for the next session. Thanks to all of our speakers for those really interesting, provocative and informative talks. Thank you.
Silvina, Hondro, if you are online, just to get ready for the next session. Hi,
yes.
Hondro.
Hi, yes.
And I believe I saw Silvina online as well.
Yeah, she's there.
Yeah. And we have our first speaker. I can see Christy just primed to share screen.
And sorry, Nico, I didn't send you my slides.
That's fine. I'm sure it will be without any problems.
You want me to put them up now?
Yeah, if you want, because then we can avoid. Yeah, and then Hondro is here already, so we have one of the chairs, and whenever Silvina.
Good to see you.
Good to see you too.
Mr. Everyone, cheer for coming.
I appreciate the invitation. It's been interesting listening.
Did you have fun in working group too?
We finished. It's a very different dynamic doing a plenary on Zoom versus doing it in person.
It is very different. And I
Really?
hear there were some challenges.
Yeah, it just, you don't have the usual socialization of the issues at coffee and over lunch. And so some things get to be bigger issues than they need to be.
Well, you can still actually do a lot. I mean, considering that we are sitting in this now for 2 years, I think we actually accomplished quite a bit in this way. And to some extent, we have more than 100 people online. I think in the Hamburg workshop, we had 30. So I think it also has some benefits.
Oh, it definitely has some benefits, but doing an approval session on Zoom is really significantly challenging.
I know. But then, of course, Pierre's carbon footprint always lingers around the corner.
Good. But anyway, I am not the kind of chair. I don't know who's the chair this time. I forgot.
Sabine?
Silvina and Hondro. Hondro, if you want to take it over, or Silvina.
Yeah, thanks. Welcome back, everyone. Welcome back. Welcome back to this session 3 on societal needs for climate information. Me, Runstina Barmalal, and Silvina Solman will be co-chairing this session. We'll have 5 consecutive talks, 10 minutes each, and then 10 minutes discussion at the end. And we encourage you to jot your discussion and questions in the Etherpad, so we'll get back to them during the discussion time. Silvana, yeah, are you around?
Yeah, here, I'm here. Hi, thank you, Rondro. Let's start. We have our first presentation by Christy Eddy on health impacts. So please go ahead, Christy.
Good afternoon, everybody, and thank you very much for the invitation. I really appreciate it. I have all of 2 slides, so I'll certainly be done within 10 minutes because I wanted more time for questions. When we think about the health risks of a changing climate, these 2 sets of figures summarize the state of knowledge about current impacts and future projections. And the right also talks about adaptation. On the left, I don't need to tell you about climate change and the fact that climate change interacts with a broad range of other factors. And all of the factors I've listed, plus a lot more, are really important for understanding the current impacts and the future risks for health of a changing climate. On the left, you can see the exposure pathways that we typically look at in environmental health. Underneath is a short list of the kinds of health outcomes that are of concern. I have the privilege of spending a fair amount of time in low and middle income countries working with ministries of health. And these are all the issues that they deal with. One of the challenges we face, frankly, in health is that there are policies and programs in place for all of the climate sensitive health outcomes, and they tend to be stovepiped. That you have a maternal and child health program that's separate from your foodborne disease program, that's separate from the cholera program, that's separate from the dengue and malaria program. And of course, climate change cuts across all of these issues. So I think that we're going to see big changes over the next few years in how ministries of health approach issues, because climate change, along with some other risks, such as poverty, cut across issues in so many ways that having stovepipe programs just will not be as effective as we need them to be. I'm going to assume everybody is aware of the burning embers. If anybody is not, could somebody, I can't see the chat when I do full screen. So if somebody could just let me know, should I talk about the burning embers for a minute? Yes, no?
I sort of think you can assume that everyone understands it, I think.
Okay, then great. That's a minute I don't have to spend. These are burning embers for health. The 6 health outcomes were chosen because these are evidence-based. They're based on the projections. And those are the 6 health outcomes for which there were sufficient number of projections to actually construct the burning embers. There weren't enough, for example, for undernutrition. There's, I think, like 2 or 3 publications. And so these are not necessarily the most important health outcomes, but they're the ones where there's been the most investment in trying to understand how climate change could affect for the infectious diseases, their geographic range, their seasonality, their intensity of transmission. And we developed 3 adaptation scenarios. The middle one under SSP2 is a world, of course, that continues to kind of muddle through. SSP1 is a world aiming sustainable development. SSP3 is a world that has very high challenges to adaptation and mitigation. And so you can see at a glance that temperature change matters and our development choices matter as well. Specifically for this workshop, in terms of what kind of weather and climate data are needed, this is an outline of the research agenda overall for climate change and health, starting with quantifying the current magnitude and burden of climate sensitive health outcomes. You can see from what we did with the burning embers that in fact there's relatively little information for most of the climate sensitive health outcomes. We do need to do detection and attribution studies. A few have been done. Mostly they have focused on heat. There's a lot more that needs to be done to look at what the current burden is. Projections, you've talked about finer scale modeling. You've talked about the importance of adaptation. Those are critical for health. In terms specifically of adaptation, there's lots of interest, not a lot of investment, but a lot of interest in taking more climate information and use it to develop, for example, heat wave early warning and response systems. And that is focusing not just on population health of how many people, for example, could be affected in an outbreak of dengue fever, but also healthcare facilities. Too many healthcare facilities are located in vulnerable locations. Typically, it's quite expensive to build a healthcare facility, and they're often built on marginal land because it's cheaper. And that has consequences for what happens. We also have to think about how healthcare facilities can manage extreme weather and climate events. I live in the Pacific Northwest. The heat dome that hit here last June resulted in a 69-fold increase in hospital admissions. We had a webinar about that event, and our healthcare facilities managed, but it was a just thing. It was pretty close call in some places. on whether they'd be able to manage the number of people that were coming in. Part of the challenge we had is that there was no early warning system here. There were meteorological forecasts, but there was not a system at the city or county level on what to do with that information. There's a lot of opportunities, particularly in that space, that health has been relatively slow to pick up on weather and climate data. We know from some of the early warning systems that have been implemented that they can be really effective, and more collaboration between climatologists, meteorologists, and health professionals would result in a variety of advances to improve health today and protect it in a changing climate. Estimate the cost to individuals and health systems. I'm sure you'll hear this from the other sectors as well. The better we're able to estimate, I think I said able twice, the better we can estimate cost to individuals and the health systems, we're going to be able to encourage investment. Overall investment in climate change and health is truly extremely low. When you look at how much is invested in building climate resilient health systems under the UNFCCC, it's running at less than 0.5% of what they've invested. When you look at research dollars, it's running even less, unfortunately. And the last is something that I think be interesting to pick up on in the chat. I know you've got a lot of focus in the discussion, rightly so, on mitigation.
2 minutes. 2 minutes, Christy.
And the studies that have been done show that the health benefits of mitigation, getting more people walking and biking so there's less urban car trips, reducing exposure to point sources, and encouraging people to eat only as much meat as their doctors recommend. For all of those, there's significant health benefits, and one can quantify the numbers of avoided hospitalizations, the numbers of avoided premature deaths. When you value those, the value of health benefits of mitigation policies are about the same order of magnitude as the cost of mitigation. We should be mitigating for our health. With that, I will stop here and yield my time back, so we have more time for discussion. Thank you.
Thank you, Christy, for the interesting reflections. And thank you for limiting the time of your presentation. So we will go for the next presentation. It's about carbon budgets and communication. And I will present Robert McSweeney to go ahead with the presentation, please. I will let you know when you have 2 minutes left.
Great, thank you very much. So hi, for those that don't know, Carbon Brief, where I'm from, we're a group of journalists that report on all things climate science and policy. So I'm going to use my few minutes to talk about how carbon budgets have been covered in the media. Unlike Christy, I've got loads of slides, but I'm going to whistle through them quite quickly. So over the last decade or so, carbon budgets have become a prominent tool for informing climate policy. One of the key benefits, as these quotes highlight, is that they provide a simple way of bridging that gap between climate science and policy, being used, for example, as a basis for net zero targets. It's interesting to look at whether this simplicity translates when carbon budgets are reported in the media. So this is the earliest mention in the media I could find of a global carbon budget in this context, from a database called Factiva. Here, Reuters is covering a Greenpeace report in October 1997 called The Carbon Logic, which calculates a remaining carbon budget for 1 degree of warming. Interestingly, their figures came with an uncertainty range of plus or minus 50%. So if we skip forward now to 2013, the year of the IPCC AR6 Working Group 1 report, and mentions of carbon budgets in the media are still predominantly related to country level budgets and individual carbon footprints. That said, organizations such as the International Energy Agency and Carbon Tracker have now calculated their own global budgets. So this quote here comes from a column by a Reuters energy journalist called John Kemp. So then later that year, we get the IPCC report, and I've included the table here from the census report, which is obviously the year later, but just because it's easier to see the different variables that they included. So you've got 3 warming levels, 3 different percentiles for each warming level, and then each are based on a couple of different approaches, and you've got a couple of different time periods presented. So, of course, the IPCC makes a huge difference, and carbon budgets are kind of propelled into the spotlight. So here we have the New York Times reporting that the IPCC endorses, in its words, global carbon budgets for the first time. And then conversations about carbon budgets in the media and beyond then really start to take off. I've included a few examples here from 2013. And we've got some from the UK, the US, and China here. And within a couple of years, global carbon budget has become firmly established in climate policy. And as Oliver Gedden points out here, and it's frequently mentioned in the media. By this time, at Carbon Brief, we're using IPCC budgets to provide annual updates using global carbon project data, as shown in this graphic. And indeed, those figures even made an appearance on John Oliver's show in the US called Last Week Tonight. So then we get the Miller et al. Paper in the September of 2017. And this triggers something of a tsunami of media coverage. So we'll start with the positive stuff. Here we have some headlines that tend to focus on the finding that we might have a bit more breathing room for 1.5. But then things take a bit of a turn in the Times. The Times puts the story on its front page and continues on to page 2. I'll read you the opening line, or a couple of lines. It says, the worst impacts of climate change can still be avoided, senior scientists have said after revising their previous predictions. The world has warmed more slowly than had been forecast by computer models, which were on the hot side and overstated the impact of emissions, a new study has found. And that second headline on the slide there is the one for the online version of the story. Things get worse in the Daily Telegraph, which also puts the story on the front page and continues on to page 2. So their opening sentence is, climate change poses less of an immediate threat to the planet than was thought because scientists got their modelling wrong, a study has suggested. So that's both the Times and the Telegraph focusing on 2 particular elements of the story, climate models and scientists supposedly being wrong. And there's more, I'm afraid. Here is page 2 of the Daily Mail and an editorial from the following day. The story leads with a line that the threat of global warming is not as bad as previously thought, climate scientists admitted yesterday. And the editorial begins with, for the umpteenth time, climate change scientists have been proved wrong, with evidence of global warming falling short of their alarmist predictions. It very quickly pivots to a favourite topic in parts of the UK media. And it's this quote here, yet not a whisper of apology do they utter for their swinging green taxes levied on energy bills, or the landscapes and sea views destroyed by unsightly wind farms on the strength of their prophecies of catastrophe. So in the same paper, next to the editorial, the day after the study, the Daily Mail also included this full-page comment piece by Labour MP Graham Stringer. So for those that don't know, Stringer is a trustee of the Climate Skeptic Global Warming Policy Foundation. And just last week was slated to join Nigel Farage's now cancelled anti-net zero rally this Saturday before pulling out. But he writes, the importance of this new investigation cannot be downplayed. It shows that so many of the assumptions behind the imposition of the fashionable eco agenda, such as the creation of vast subsidised wind farms or the levying of green taxes, are very wrong. Yet the environmental warriors show not a shred of embarrassment over these new findings. And then on the right, we have a news piece in the same edition, which again shows the focus immediately shifting from the debate about carbon budgets and onto green taxes. Not wishing to labour the point, but here are a few more examples, not just in the UK media, but also from US outlets such as Breitbart and Fox News. There were, of course, numerous pieces pushing back on this coverage and how it mischaracterised the study. Carbon Brief alone published 3 articles on just this paper, along with several more before and after the IPCC's 1.5 report in 2018. Thank you. This is my last slide. And so there's been a lot of work since then, unpacking all the factors that affect carbon budget estimates, as this figure highlights. And I also think this quote from a Carbon Brief guest post by Yuri and Piers sums up the kind of post AR5 journey for carbon budgets quite nicely. But I think fundamentally, kind of looking back at this kind of media coverage, the way that certain sections of the media reacted to the Miller et al. Paper, it wasn't really about carbon budgets, but it perhaps highlights how something that was supposed to be simple and transparent became something that was used to attack both climate science and climate policy. And fortunately, the media landscape has changed for the better over the past kind of decade, particularly in the UK. But as the current scrutiny of net zero targets and energy policy shows, there are prominent voices that will seize on an opportunity to undermine action on climate change. Thank you very much.
Thank you, Rob. Interesting view of what the media shows about our carbon issues. So next, and thank you for the presentation. Next, move on to the next talk, Mitigation, the IPCC Working Group 3. And the presentation will be shared by Joeri Rogeli and Maite Meinhausen. Sorry if I pronounce your names and surnames wrong.
That's very good. Thank you very much. And thank you for the opportunity to present here. Basically, under the radar of IPCC Working Group 3, who is now in their approval plenary, virtual approval plenary. But I'm very glad to be able to give some insights or some food for thought on what the mitigation community can use in terms of climate information from the climate modeling community. I will be sharing these. The slides are been prepared by Malte and me, and we'll be sharing the presentation. Just of the presentation, there basically I think there are 3 key questions that the mitigation community asks from Earth system, and that is how much warming for a given pathway of emissions. Then, are our mitigation strategies resilient to climate change? And a last question that really looks at how we can better integrate Earth system science and knowledge in climate mitigation studies is basically the question of what can be done to improve that integration. If you think about mitigation, many climate scientists think of the right-hand side, which is basically the large set of scenarios that are available and are developed by the mitigation community, and from which, for example, the scenario MIP exercise has drawn its key simulations. But of course, mitigation community is much more than just those scenarios. So let's have a look at these 3 key questions. The first of which, how much warming for a given pathway of emissions? And if we think about this question of what are the key pieces of information that the mitigation community would like to see or get from the climate community, well, the first of those is more information on the climate response to emissions. Carbon budgets, or maybe the TCRE more precisely, would be really useful. The previous presentation has really clearly indicated that carbon budgets are really just a 0 order or a 1st order tool but for many mitigation modelers, for many people in that community, they are still the single tool they use to define whether their pathway is consistent with a certain temperature outcome. Further information is also absolutely necessary to better understand the warming from non-CO2 emissions, both the greenhouse gases and the aerosols, still key uncertainties in our projections. And as we are also looking more and more at deep mitigation scenarios, it would be really important to get more insights in emission-driven runs that provide a better quantification of what the carbon cycle and carbon cycle feedbacks do at quite low emission levels. Also, to understand how much we can still emit or how we can transform to limit warming to international temperature limits, we need to understand better also our history. And for example, some climate runs starting from 1750 in order, or pre-industrial, to better understand that warming would be useful pieces of information. Second part is there how reversible warming is. And now we're really thinking just about the geophysical reversibility, not yet about what it means for ecosystems and so on. We think about the zero emission commitment, expanded maybe to all greenhouse gases, also understanding the Earth system response to net negative emissions, or with the link to UN climate policy, what will global warming do in a net zero greenhouse gas world? And here on the right is our current understanding of what that would do, but as this is a key part of the policy discussions, also more information and more insights there would be useful to understand the implications and the outcomes of the mitigation pathways that this community is developing. Then what would be also really useful, and Pierre already highlighted it, we can't just run the most expensive models for all our applications. So the availability of lean and flexible Earth system modeling tools that allow the translation or the operational application of Earth system model insights in the mitigation community would be extremely valuable. And also they allow us then to combine uncertainties across the various domains of expertise, be it carbon cycle, climate, and other areas. The second question, and here I will go a bit faster to leave some time for Malta as well. Are mitigation strategies resilient to climate change? This is basically the question of integrating the adaptation and research of the adaptation and mitigation community, where it is key to get information to understand whether the infrastructure and the systems that are being designed in the mitigation community are indeed reliable in a world under climate change. For example, it is important to better understand the effectiveness of a variety of land-based mitigation measures under climate change or other Earth system constraints, for example, nutritional constraints. And handing over to Malta now.
Thank you, Yuri. Thank you, Silvina. And so the question is then really, if we have $10 billion or if we have $3 billion, how much do we focus on the Earth system models? And you can advance through the slide. How much do we spend on the Earth system models and make them really run policy relevant scenarios? And there, it's important that we run not purely academic scenarios. Yes, they're interesting. They're interesting to gain our advance our system understanding, but an overshoot scenario SSP 534 is very much irrelevant for the real policy world that looks at, do we aim for net zero in 2050? Do we aim for net zero CO2 emissions in 2060 or in 2040? And so there, it would be great to have a good fraction of the resources really focused on the policy relevant scenarios, and TCFD was mentioned before, and the financial world is looking at those. Look at the whole post-processing chain, and that is the second point here. You can advance the slide. focus on the scenario design and the methods that are particularly useful to combine the knowledge across all the different domains. And think about, they're also about, it was mentioned before, the combination with observations. Like there's so much more needed after we have high resolution ESM output to make it really useful for policymakers who ask the question, okay, what is the benefit of us going through this decade for deep mitigation? What is the benefit in terms of my local agricultural yields, etc.? And so combining the whole chain, both in terms of adaptation and impacts, but then what does it mean for mitigation? How much more mitigation do you have to do to avoid these kinds of impacts? We need that post-processing chain. And so there are some experiments needed to really flesh out the impacts of different species, emission and removal experiments, different land surface changes. And there, of course, it's a pole between doing less policy relevant, more academic ones, but they can be used to then train emulators that then can close the whole cause effect chain. Yes, we heard great presentations by Lena and Sabine on floods and land surface models. So how can we combine them in a useful way with the key variables that are of relevance? So, and this is really where the lower point, we need to invest something in better emulation tools that can go across the whole cause effect chain. Last slide is just a summary. As Yuri mentioned, we have we need to get from Earth system models the great one-way forward street of how much warming for a given pathway of emissions and quantifying the carbon budgets better, then making mitigation strategies resilient to climate change, land surface and negative emissions is the key point here, and preparing integration. And it's not only integration, it's just the whole post-processing chain. If we spend $3 billion, we should spend a sizable amount and not maybe just 10 million, what I would estimate at the moment at the post-processing of getting tools ready that combine everything and make it available for the thousands of scenarios that are run by Working Group 3. Thank you.
Thank you very much, both, for the interesting presentation to both of you. So let's move on, and then we have now Chris Leonard making a presentation on the IPCC Working Group 2, Impacts and Adaptation. So please, Chris, go ahead.
Thanks, Silvina. Nice to see you again. Thank you for the opportunity to present the IPCC Working Group 2 perspective. I'll try and stick on time. So the Working Group 2 is the Working Group on Impacts, Adaptation and Vulnerability, whereas Working Group 1 was the physical science basis. And I think the majority of this audience sits in the Working Group 1 context. So I hope that the Working Group 3 talk earlier and this talk will hope inspire you to do some work that's applied in our working groups. So the major takeaway message of our working group was the scientific evidence is unequivocal that climate change is a threat currently to human well-being and the health of the planet, and that any further delay in concerted global action will miss this brief, rapidly closing window to secure a livable future, and that this report offers hope to the world because we do offer some solutions. Global warming has caused dangerous and widespread disruptions in nature, and climate change is affecting the lives of billions of people despite efforts to adapt. The impacts are magnified in cities where more than half the world's population lives. So here's a nice challenge perhaps for large urban scale modeling for this community. But also that simultaneous extreme events compound risk. Multiple extreme events compound risks. They're more difficult to manage. So if you have two extreme events happening at the same time, or you have consecutive extreme events, these are the types of information that we need in a working group 2 context when we talk about adapting to these types of risks. Because 3.3 to 3.6 billion people live in hotspots of a high vulnerability to climate change. And this is a map of that. They largely are across the tropics. And in Africa, it's east, west, central, and southeastern Africa, parts of Africa, and then over the Indonesian islands too. So understanding tropical and subtropical climates are really important. So can you point the climate models in that direction? Do you resolve the processes there well? And we end on this. To avoid mounting losses, urgent action is required to adapt to climate change, acknowledging that at the same time it's essential to make rapid deep cuts in greenhouse gas emissions and to keep the maximum number of adaptations open. And when we talk about adaptation, and there are two other working group 2 authors on this, so yeah, you can correct me if I'm wrong here, Brian. The goals of climate change adaptation is a broad concept to reduce risk and vulnerability to climate change, to strengthen resilience, enhance well-being, and to enhance the capacity to anticipate, respond successfully to climate change. So climate modeling speaks to climate change adaptation, all aspects of adaptation. So there is definitely room for climate modeling to contribute to the working group 2 process. And our future looks, it's in terms of reduced climate risks. So we're going to need to reduce climate risks. So there is adaptation that is needed. There's a reduction of greenhouse gas emissions that is needed, so mitigation. And enhanced biodiversity is part of our future because this biodiversity is a very large part of the adaptation mitigation process. And this is all achieved in some of the sustainable development goals that we have. And when you put all of this together, we get what's called climate resilient development, which is a process of implementing greenhouse gas mitigation and adaptation for all processes. And CRD draws on wide-ranging knowledges. It is scientific knowledge, indigenous knowledge, local knowledge, and practical knowledges, conserves and restore ecosystems, which is part of the solution. It involves marginalized groups. So it is an inclusive process. It doesn't put some folk on the side and prioritizes equity and justice. It reconciles different interests, values, and worldviews. So there's not one dominant worldview that determines an agenda. And it requires scaled up investment and international cooperation. And this cooperation is really important in many different contexts. So how can climate modeling then contribute to CRD? And here, what you're going to get now is my opinions based on the working group 2 text. It's not the official position of the IPCC working group 2, so please keep that in mind. Within CRD, there are various challenges and opportunities with respect to the production of climate information, which is needed to make adaptation decisions. And therefore, we assume that that information is based on climate modeling. And one of these opportunities and challenges we heard earlier from Chris is about early warning systems and climate services, and these in the context of drought, of heat, disease, flood. Developing these early warning systems is really important, particularly in developing nations and in large city contexts. So modeling at relevant time and space scales for early warning systems is a challenge perhaps for the climate modeling community. Then there are uncertainties in climate and socioeconomic projections. These uncertainties constrain the ability to plan for adaptation and the implementation of adaptation. There's also uncertainty in future water availability for consumption, food and fiber, and for energy, and uncertainties around ocean modeling. And that's important for fisheries because large coastal communities are still dependent on the oceans for their food. So can this uncertainty space be constrained, or can it be better understood so when adaptation decisions are made, we actually understand that uncertainty space? There are also challenges related to REDD+ implementation and forest use, so the land use work that Elena spoke about earlier. Then there are also changes in means and extremes that these disruptions to the natural environment can disrupt livelihood practices and cause people to out-migrate to urban centers. And these changes in the extremes in particular is where we need a lot more information. It's how do extremes change? Renewable energy is another opportunity actually, because if we can do really good renewable energy resource exploitation, that can offset a number of health impacts. So renewable energy is another opportunity for the climate modeling community to get involved in. And then the appropriate use of climate information. What are climate models? What can you use them for? What do they not say? And this helps in avoiding maladaptation. So can climate modelers engage with user communities to talk about that? Then the last thing I'll mention is the challenge with global warming levels. And here we know global warming 1.5, 2, 3, and 4. We understand what the impacts of these global warming levels might be, but as adaptation planners, we want to know when. So not having a time axis on when do we hit 1.5, when do we hit 2, when do we hit 3 is really important for us for an adaptation planning horizon. And I've just, as a last thing, thank you, Silvina, as a last thing, included that reference there, improving the contribution of climate model information to decision-making. It's a nice paper to read. So in summary then, and again, my summary, not IPCC summary, first thing I think is to reduce or improve our understanding of the geophysical aspects of model uncertainty. So really trying to narrow or understand better that uncertainty space. 2, global warming impacts disproportionately around the tails of the distribution. So understanding more about the extremes in the tails. Then climate modeling can contribute to timescales that are relevant for adaptation. We don't care about 2050, 2100. We're sitting more in the S2S, maybe the seasonal to decadal, and maybe out 30 years or so. So I understand those are the difficult timescales to get at. Then the involving marginalized groups, and this for building capacity for climate modeling. And this was a sad thing to see when I looked at the agenda. Of the 27 speakers in this meeting, only 3 are from developing nations. 2 are in this session. There's only 1 developing nation science talk, if you like, climate modeling talk, and that's from Francois tomorrow. Then 5 is reduce the uncertainty around when global warming levels might be crossed. Mentioned that as the last thing earlier. And then 6 is to give the working group 2 in an IPCC context for CMIP, whoopsie, give the IPCC working group 2 literature time to catch up to the working group 1 literature, because the CMIP cycle starts, CMIP 6 starts, working group 1 gets the hold of that data, does all the climate assessment, and only then does working group 2 come along and think, oh, look, there's CMIP 6. So in our working group 2 context, we were assessing largely CMIP 5 literature, not CMIP 6, whereas working group 1 was assessing largely CMIP 6 data and CMIP 5. So working group 1 lags working group 2 by a whole CMIP. So if we can line that up, that would be really helpful too. And there was a 7th thing that's right at the bottom of the slide, but I can't remember what that is. So I'll end with this next one. Here's the CMIP 6 deck. And my appeal, I guess, as a working group 2 person would be, if you have time and resource, to zoom in on that impacts piece of the pie, because for development of adaptation options that is useful for people and valuable for people, that is where we need to look at. So thank you for your time. Thanks for listening. And yeah, thanks, Silvina.
Thank you, Chris. Very interesting presentation as well. So let's move to our last presentation of this session. Is run by Mandira Shrestha, and the topic is communities in the global south. So Mandira, are you ready? Please go ahead.
Okay, can you hear me, Silvina? Yeah, yes, you can hear
me? Yes. Please
okay.
Put the presentation mode in your
Can you see it in presentation mode as well?
No,
okay, good.
Not yet.
Well, very good morning, afternoon, evening. This is Mandira Shrestha from the International Center for Integrated Mountain Development. We're located in Kathmandu, Nepal. And just a slide on my organization. We are a regional mountain knowledge organization. And we primarily work in 8 countries in the Hindu Kush Himalayan region. And those 8 countries comprise of Afghanistan, Bangladesh, Bhutan, China, India, Myanmar, Nepal, and Pakistan. So
Mandira, could you put the presentation mode, please? Because it's not, or at least I cannot see the presentation mode.
Oh, it's is in presentation mode in my computer.
No, I don't see that.
Well, it is not, and it's not advancing. So maybe, Nico, you need to do this.
Okay, let me just, yeah, it's not advancing. I can see that. Let me just hold on there. If you will allow me to just, it just seemed to have frozen. Okay, can you see it now? Is it it is advancing now in my computer, but is it advancing in yours?
It is not. It's stopped in the slide number 1.
Mandira, if you want to send me, it's Nico here. If you want to send me the slides, then I can play on my end.
Now it moved.
How about now? I try once more again, And if it does, then good. If not, I send you, Nico. Is it okay now? Silvina?
Slide number 1. We are seeing slide number 1.
Yes, but are you seeing in full screen mode?
No.
No?
No. Maybe the connection is too slow, and that is why it takes so long to move from one slide. There we have the second slide, but it's not slide presentation mode yet. But go ahead like this. We can follow you anyway.
Okay, good.
Okay.
Thank you. So the Hindu Kush Himalayan region, for those who are not familiar with our region, we extend, basically across 8 countries, like I mentioned, and we are, the largest reserve of ice and snow outside the polar region, given us the name also as the third pole. The largest river basins emerge from this region, and we are, 4 global hotspots exist in this region. So it's extremely an important region in terms of resources, feeding more than 240 million people in the region, as well as about 1.9 billion people living in the downstream. And that, if you're talking about the world's population, is about 35%. So it's a huge population that it feeds on. Now, some of the key issues of our region, the Hindu Kush Himalayan region, is that primarily we live in a multi-hazard environment, and whatever happens in the upstream very much impacts those living in the downstream. And climate change and variability is having profound impacts on our resources, as well as the human beings' livelihoods. And the connectivity and physical access is quite difficult given the very challenging terrain that we live in, and institutional mechanisms and governance is also an issue. Now, in terms of the climate context, I think what is being discussed today is that, we're talking about the 1.5 degree world, or, the 2 degree world. But when you're looking at the 1.5 degree world in general, for the Hindu Kush Himalayan region, it's much warmer. It's even, 1.8 or even higher, 2.1, since in the mountain regions, there's more temperature dependent warming. And there was a study that was done, the Hindu Kush Himalayan assessment about a few years ago, and it's like a mini IPCC for the region, and where, the findings were showing that there was a lot of warming that was happening in the region as a result, that leading to a lot of possible extreme and erratic extreme events. So that's on the rise. Now, since this is the top of the world primarily, so what happens here is affecting 1/4 of the humanity. So therefore, we need to really protect the pulse of the planet. This is the region. And according to this study that I mentioned, if you're talking about a 1.5 degree world, the glaciers in the Hindu Kush Himalayan region will lose 1/3 of the volume by 2100. And then if you're looking at it business as usual, 2/3 of the volume under the current emission scenarios. So therefore, this will have profound impacts, possibly in terms of the disasters, in terms of the glaciers and glacial lakes that are increasing. Therefore, better preparedness, better models, and needed early warning systems are needed in order to build resilience and mitigate these adverse impacts. So in general, in the region, we see that 1/3 of all the disasters are from floods, and that the economic impacts are increasing. Many of them are transboundary, so it's important that information is shared across borders. I'll give you some examples. I think it was mentioned about cascading events earlier. Hazards. So these are some of the examples of these extreme events that occurred just in 2021, where, for example, the one in Uttarakhand, where there was a huge disaster, a rockfall that occurred in the upstream, which results in a large flood, wiping out a number of infrastructure. Similar disasters are occurring in Nepal also. These are cascading events. I think, and understanding this event, it's not only about one type of extreme, it's multiple different events that are happening, which is even making it more challenging in terms of prediction of such kind of disasters. So there are a number of challenges. Definitely, it's about increase in the intensity and frequency, but one of the challenges, given its remoteness of our region, the network densities that we have is quite limited. We have limited sharing of data and information. The capacity of modeling and using of these tools are varied, and much of the information that is being generated needs to be tailored, and many of it is not tailored. I think the previous presenter Chris mentioned about, the need for also including and being more inclusive. So it's important that we also look at gender aspects and for responsive climate services. And so I'll not go into details of what climate services means, but I think we need to also keep in mind that we're talking about the entire chain from where, it's not only about the producers per se, it's about, also it's delivery, packaging, and the use by different stakeholders, the policymakers and operational agencies. And that's what the focus of this particular session is to look at the user perspectives of these services. So the different temporal scales, spatial scales is important, what we're talking about at the global and the national levels, but more important is at the local level, more at the beneficiary levels, and then the temporal scales from the weather time scale to seasonal to climate time scales, for which different products needs to be customized for the use of those users. There are different climate sensitive sectors, we're all aware of that, and that the one that I'm particularly emphasizing here is on the disaster aspects, as well as the agriculture actually. And then the opportunity, yeah.
2 minutes, thank you.
Okay, so there are plenty of opportunities in terms of building these capacities across the region and using of specific tools and technologies. This particular slide shows you this this framework for reducing risks in terms of in the 3 components: hazard, exposure, and vulnerability, and that we're looking at different components in terms of increasing knowledge, partnerships, using science and technology, ecosystem resilience, and gender mainstreaming. So in order to do that, through the Climate Services Initiative, we're working in partnership with many different organizations, strengthening capacity and user engagements. So institutional capacity building, particularly the role of climate projections and its applications has identified as one of the key important areas. We've been working with the Met Services of UK, and here we've had series of consultations with various organizations. And I think the importance is in terms of really looking at co-generation of these knowledge and information. At the local scale, we understand that the user landscapes really need to be mapped and understood, and gaps need to be identified, and also building of the awareness at that local level and customizing the products that we have to reach out to these end users is essential, for which capacity building and in understanding these products are essential. So finally, the second last slide I have, we've also developed these modeling tools for various users, particularly the hydromet agencies, but also this use for advisories at the local level, like for instance, flood forecasting using earth observations and various tools and capabilities. And some of the needs and priorities that we have, use of, so for example, the Cordex data sets in the region has been quite interesting. And that what has been sounded to us is that the need for capacity building using these tools, whether it's for assimilation, whether it's for forecasting, whether it's for impact-based, and then the using of finer resolution models, the institutional capacities in terms of access and use of these climate projections and its applications, and then the co-development of some of these products for specific needs of the users, particularly to reach out to the end users for the societal benefits is important. What does it mean to the farmer? For instance, the use of some of these projections, or to the planner. How can they use that better? I think those need to be tailored in such a way that they can understand it. And this is one of the major challenges that we have as scientists, or the providers, to really bring that information down to those that are actually the beneficiaries and that needs to be benefited. So enhancing capacity, improving communications, dissemination of these products in the language they understand, sociocultural norms, settings. It's not always the same in all the countries or in all the regions. You have to be sensitive about the sociocultural norms to better communicate the products to the end users, and then also put in place, these products so that they can support adaptation planning and decision making. Yeah.
Thank
so
you. Thank you, Mandira.
And that, Sylvia. So thank you very much. I have much more to share, but I know time is limited. So thanks a lot.
Sorry. Thank you very much. Sorry for cutting again, but we need to stay on time in order to have everything on board. So thank you for all the presenters for these very exciting sessions. Now, as Helen suggested, we have 10 minutes questions and answers, and we will start with a question from the floor. So we will use the hands up facility of the Zoom, so you can make the questions, and then if there are no many interactions, we will go with the questions that you raised in the Etherpad. So I open the floor for questions. So whoever wants to make a question, Detlef, go ahead.
Yeah, thank you. First of all, thank you actually to all the speakers. I found this actually an extremely inspiring discussion, both parts, before the break and after the break. In fact, the discussion after the break is somewhat new to me, and so maybe that's why my question might not be too informed, or I apologize a little bit, but I had actually a little bit difficulty, and maybe from the discussion on Etherpad that the answer might be clearer, but it's still useful, I think, for me to have a brief discussion. To what extent, and this might relate to all the speakers, is it really improved models that you need, really a model development, or is it more a development of tools or of diagnostics, or in some kind an afterburner, like an early warning system that actually would work very properly with the existing output, for instance, for Christie? This wasn't really too clear to me to what extent you really need different models, like what Tim was suggesting, a 1 kilometer global ensemble of long climate runs, or would actually the existing CMIP runs, just as an example, be quite sufficient if you would have the proper diagnostics and maybe the interaction with the modeling community to develop the early warning system that we heard in several places. So this is maybe just in a nutshell the question: how much model development would you wish to take place, as opposed to how much post-processing, like Maite, for instance, said?
It's a good question, and I didn't specifically address that because it depends on scale, both temporal and geographic scale. Developing an early warning system, you want information on a pretty fine scale, but you're not going to use a model to develop an early warning system to make projections. And there has been confusion in the health community about modeling and thinking about the different temporal and geographic scales. I think what's most important in the short term is to develop much better collaborations between your community and the health community. There's way too many publications coming out of your community, not involving health researchers, that have serious flaws. And equally true on the health side, people going out and using climate information and has serious flaws. So I don't want to give one answer on the model, because it depends on what it is you're trying to achieve. And mostly we need to work together to make sure that we have the most appropriate data and models on both sides. And we're pairing those up in the most effective way.
Okay, thank you very much.
Thank you, Detlef and
Sylvia, can I just
yes, Mandira, please go ahead.
Yeah, I think it is both, in fact, the parallel process, because we have the challenges of really meeting the needs of very fine models applied to very difficult terrains and topography where general models do not really apply. So generalizing it in a small scale is quite challenging. But at the same time, whatever we have right now currently is also to some extent sufficient to really reach out to the users. But having said that, it needs to be customized so that it is understood better. It is communicated better, because there's always that gap between the understanding and the communication to those that are actually using it. There's a lot of scientific information, but really using it in a way that could be helpful to the society is the missing link at the moment. That bridge needs to be there. So yes, better communication between users and providers is essential for that. But at the same time, yes, enhancing the knowledge, better finer resolution models is also important, particularly for these difficult terrains in which we live in. Thank you.
Thank you, Mandira. And now, Sabine, your answer.
Yeah, thank you. So I definitely vote for answers that might be application specific. And I think the two cases I have shown for the flood forecasting system, we definitely need higher resolved climate models going to an hourly basis and to kilometer scale resolution. We need these online coupling that might be sometimes also technical, but also from the hydrological model side. In the past, we had so often hydrological models working only in one catchment only, and really to be linked with your world, with the climate model community, we definitely have to regionalize our models and have it globally or continentally in high resolution available. And we made the first steps. There's a community existing, but I think we definitely need a stronger collaboration between our two worlds. Thank you.
All right, thank you very much.
Thank you. Thank you. Thank you all for this discussion. I don't see more hands on. So Rondro, do you have any burning question on the Etherpad?
Yeah, I think the discussion in the Etherpad, it's really going, it's very, very active. I think one of the main question is in Christie's part, like what kind of data do you need? What kind of information do you actually need that the climate modeling community could provide?
I think I already answered that. If you're, I put in the slide, the figure that shows how many different health outcomes we're thinking about. And what we need for heat is different than what you need for dengue fever. It's different than what you need for malaria. It's different than what you need for diarrheal disease. And so we have to get into the specifics of what issues we are focusing on at what geographic and temporal scale. If I'm looking at falciparum malaria, it's sub-Saharan Africa. And having much better fine-scaled information than what we have for sub-Saharan Africa is on just about everybody's agenda. If you're looking at dengue fever, it's another set of questions. So unfortunately, I'm not going to be able to answer that because we don't have one answer across all of those health outcomes.
Thank you, Christy. I see more hands on. It's Krishnan, then Chris Leonard, then Paul Durack. Okay, Krishnan, please go ahead.
Yeah, thank you, Sylvania. I just had one slide for session 2. Just can I quickly show that?
I'm sorry, I didn't get what you asked.
Krishna wants to show a slide.
Okay, okay. Yeah. Go ahead.
Yeah. Thank you. Yeah, this is the slide. Just I wanted to show, this is for the session 2. We see the CMIP 6 has done a wonderful job, lot of valuable data. But one thing is what we are seeing is large biases in the South Asian monsoon precipitation, which has existed right from CMIP 3 and CMIP 5. So the thing is, if we have this type of biases, because also the latent heating is going to be affected, and which can affect the tropical circulation and also assist the sea surface temperature gradients. So the entire coupled system gets into this vicious cycle of biases propagating across different scales and ESM components. Question is, how do we urgently reduce these biases? So these are questions I don't know the answer. So is ultra high resolution cloud resolving model without parameterization coupled with the ESMs, is that a solution? Or whether you have to use AI ML techniques because we have no lot of satellite data for convection parameterization. So thank you very much.
Thank you, Krishnan. I don't know if this session, the presenters of these sessions are the key people.
Okay.
Question. Maybe it's a session 1 question. I would imagine. Yeah. I don't know if is there anybody who wants to answer to.
Well, Selena, it's probably a session 2 question to Tim,
okay.
Session 2.
Ruby, or.
So, is there anybody wanted to answer to him?
So Tim Palmer here. I mean, just on the AI, I mean, you know, there's an underlying problem, which is that parameterization, you know, the basis for parameterization is weak, particularly for things like convection. The scientific basis for representing convective activity, you know, a highly multi-scale nonlinear system by a kind of parameterized formula predicated on something like statistical mechanics is weak. And so the idea that AI could get you out of that problem, I think, is wishful thinking. I think AI can probably do parameterization much faster than many of our conventional parameterizations, but the idea that it will kind of solve the problem that we have with parameterization, I think, is wishful thinking. So the only other option really is, I believe, to you know, basically solve the laws of physics more accurately. But you know, I can't prove that, but I think we have to give it a try. I don't see any alternative. So yeah, so that's my view.
Yeah. Thank you, Tim. Thank you so much.
Thank you. I'm sorry, I misunderstood the session question. So sorry for the confusion. Chris, please go ahead. You have your hands on.
Sure, thanks, Silvina. Just wanted to add a little bit to what Christy was saying, is that it's not only in health, also, I mean, there are many communities that require particular types of data and information. So the biodiversity ecological community needs a very different kind of data to what if the health community would need. Equally, the hydrology modeling community needs a different flavor of data. So it does require an engagement with each of these different communities to understand what they need in terms of data. Their time scales work differently, their spatial scales work differently. So if we want to do it properly or more effectively than what we're doing it at the moment, then it requires that engagement. It's exactly what Christy was saying, but it's not, it's transdisciplinary, if you like. So it's not even just between scientists. It gets a bit broader and messier than that. And it's really hard to do. We found that in working group 2.
Thank you, Chris. Now, Paul Duriak, your turn.
Hi, folks. Thanks for these really interesting talks, actually. The question I had was kind of following on, I think, from discussions that, you know, Chris just mentioned this as well, but I was trying to think of an example that maybe Chris could give us of what she would think would be like an unclogger for collaboration across the working groups, or, you know, some way of actually starting this interaction between the working group 2, working group 3, working group 1 folks, you know, like trying to connect the dots and do better science so that we're not kind of all operating in our own silos and not interacting with the people that we need to get the science anchor piece right for what we're trying to achieve?
It's an outstanding question, and it's something people have been struggling with for quite some time. And it comes down to human beings work better when they know each other. And I can give far too many examples of health people who should know better, who don't know anybody in particular in the climate community, and go off and download data and use it inappropriately. Happens on the other side as well. So the more we can set up workshops, the more we can set up just ways that we can work together and get to know each other. Those of us in the IPCC community are pretty rare in terms of the wide scientific enterprise. And we do get to know another community, and we end up working very effectively together. It takes a little while to learn each other's languages, but thinking of ways to really facilitate as many opportunities as we can at all different kinds of scales, you know, from a local workshop within a country or within a city to something broader than that.
So I'd ask, following from that question then, how do we take the responsibility as, you know, working group 1, 2, 3 authors to make sure that we're glue that can pull different, you know, different pockets out? I mean, this is one of the things, if we were able to really effectively work across working group 1, 2, and 3, we could do some pretty amazing stuff. And I mean, you know, COVID's made it difficult. You know, languages make it difficult. Just the fact that we're all kind of very busy makes it very difficult. I think it's probably the major issue. But I mean, how can we use the IPCC infrastructure to do exactly that?
There's an opportunity for the outreach events, because there's often IPCC outreach events, and to think about structuring them in ways to facilitate those discussions. So I'll give an example. In the US, a very long time ago, 1999, maybe 2000, there was a workshop organized by a group of us, including NOAA, on bringing together the health and the climate community. And most of the health researchers in the US were brought into that. And I'll tell you a story that still amuses me. We decided to structure this workshop so that the very first speaker was from health, to talk about why we need to have weather and climate data. I'm standing around with the organizing committee when a well-known meteorologist comes up to us holding the agenda and said, "I'm so glad to hear that you health people are going to talk about something we know a lot about in meteorology, diseases born on the wind." The title of the first presentation was vector-borne diseases, and we meant diseases carried by mosquitoes, like dengue fever and malaria. It was a stunning moment of, so for years we had a slide that showed an arrow and a mosquito and said they're both vectors. And we really have to figure out how we're going to talk better together, because we need to do that. Outreach events to the IPCC, thinking about how to structure those to bring together different members of the community across working group 1, 2, and 3 within a country, within a region, and structure it not just as the outreach on the results, but outreach in terms of how we can start building those collaborations for the next assessment report.
Thank you, Christy. Thank you, Paul. Now it's Irasema. Your hand is raised. Please go ahead.
Okay. Okay, thank you. The question is to Tim Palmer. Besides the number of models and the high resolution models, what kind of improvements in models could be done with this kind of exascale machines? I don't know if you, Tim Palmer.
Hi. Yeah, I'm here. Sorry, Irasema. Say that again. So what kind of improvements in models?
Could be done with this exascale machines that you talked about, this high speed or very powerful machines, computers. Because you said that there is, you could do many simulations with many models or high resolution models. Yeah. But it would be useful also to improve the models in terms of process, physical process.
Yeah, I can mention one thing. I mean, I am a great believer in, you know, the use of numerical weather prediction, and indeed very short-range numerical weather prediction, to improve our processes which have to be parameterized. I think, I mean, you know, we've done work at ECMWF showing how just very short-range tendencies can, from a numerical weather prediction model, can really inform on the structure of parameterized processes. But that only really works well when there is a kind of comparable resolution between the climate model and the NWP model. So I think, you know, I didn't speak to this at all in my talk, but one of the benefits of actually developing very high resolution climate models is actually it will increase the synergy between climate and numerical weather prediction enormously, which I think at the moment, you know, somehow we're not taking adequate advantage of that synergy because the resolutions of the NWP models and the climate models are so different. So that's one that's one aspect.
Okay.
Yeah.
Thank you. Thank you.
Thank you, Irasema and Tim. And now I see Mandira's hand on. So please, Mandira, go ahead. I missed a couple of hands. But...
Yeah. Thank you, Sylvia. I think you know, the question regarding the working group 1, 2, and then the collaborations, I think that's well placed already. That's what we also try to do to improve that coordination and collaboration. But I just wanted to share with you that, I mean, I was just recently in Bangladesh providing a training on Cordex dataset access and use with the hydromet agencies there. And one of the questions that they asked me was, how can the experiences of the operational agencies be also, you know, kind of incorporated in this IPCC working group, you know, discussions and reports and findings, because they felt a little bit not included in that process. So I asked, you know, a broader question in terms of actually including the operational agencies in such kind of a process, you know. So what would that mean? I mean, yes, given the fact that they have all the experience of weather and climate and data and information, they are the custodians of all that. But again, they feel that they are not included because they do not have, you know, these journal articles or any these publications that is much required in that process. So what can be done? I just ask a very broad question to all present here that we can, you know, benefit from reaching out to the last mile, including these operational agencies, which provide those advisories and services to the various sectors and stakeholders. Yeah, so thank you.
Thank you, Mandira.
Can I, sorry, Tim here again, can I just very quickly come to that? Because I think that's a really important point. And I think that, you know, you have to remember your people that are in numerical weather prediction centers, they can see, you know, they get firsthand experiences of where the models are successful and where the models fail, you know, because the weather occurs every day and the people are evaluating the weather every day. So the problem with climate change, those of us in climate change, you know, climate change is sort of a very, you know, we'll have to wait another 50 years or so, and it's only happening once. So I think, you know, this is a problem. We get complacent about the accuracy of our climate models because we're not confronting these models all the time in the way that numerical weather prediction is. So I think bringing these operational agencies more into the kind of evaluation process of climate models would be extremely useful. And probably quite sobering for many people. So I fully support that idea.
Thank you.
Thanks everyone for the very interesting presentation. Thanks to all the speakers and for the interaction during the discussion. We are really running out of time, and I think we're going back to Detlef and Faishali now.
Vaishali, do you want to start or encourage
Sure,
another question?
Well, so definitely the questions are great, and the discussions have been great on the Etherpad, but it is getting late for everyone, and we are 7 past the hour. If anyone wants to have the last question, we can maybe allow one more, but I do think that we should wrap up. The talks, the discussions, everything has been just very, I would say, provocative, because that's the goal that we set out for. So I know Angie had her hand earlier, but Angie, it's up to you if you would like to come back, or I'll pass it on to Detlef.
I answered in the ether. Thanks, so.
Okay, great.
All right. Well, this is good to hear, and so it's really good to see that everybody is involved. And as Vaishali just said, I mean, this is day one. I mean, basically should not get too excited, and by extending it, we still have 3 days to go. And the idea of this first day or the talks was really to be provocative, but actually to stimulate the discussions of the next days. And I think all the talks were excellent. They all did it. Also, the discussion showed that there are in fact many questions. We could actually go on for another few hours if we wanted. But I think the good point, or the good stuff, is that we have 3 more days to do so, including breakout sessions. And so I'm really looking forward now to turn these kind of these provocative talks, these questions, in fact, that were raised, into a discussion, and hopefully to come out with, in fact, a roadmap for WCRP and others to including futures, that we come out with an idea, with a plan to move forward, and that actually would be really nice to see at the last days and beyond. And so let's move forward. Let's actually enjoy a nice night and sleep, and maybe breakfast for some, and meet again tomorrow with another day. And I'm really looking forward to continue the discussion. Thank you very much to all the speakers and to the session chairs, to the rapporteurs, and in fact to this intensive discussion in the Etherpad. Bye-bye.